Typically, we'll give prizes to the top 3, maybe, but you know, guests. Given that I don't know who guest is, maybe we'll give all 4 people here an extra bag. I know it's what one wants in summer school, but we will give an extra bag if you come claim it. So, unfortunately, if no one's here, they'll probably have all night, you know, coding on this thing. This will be the prediction now. Every morning we'll post these, and whoever's in the current top 3 spots, if they weren't today, will get a prize. Even if they were there yesterday, someone can start accumulating like a lot of these bags. So motivation to get on to start doing well on this, right? You start getting your name recognized, and if you're here, you can stand up and we'll applaud you. All right. So without further ado, we'll start the actual content here with Deepak's next lecture. Oops, I messed it up. That's not much good. That's strong. Yeah. Oh, okay. They work. Okay. Here's the. So this is. Okay. Can everyone hear me okay? Camera? Okay. Great. So, welcome back. So yesterday we were discussing how to do explore exploit for choosing the most popular article, and I went through the entire Bayesian solution from first principles. So today we are going to be more practical about it. So in general, as we know, we have to do personalized recommendations. Right? And so now the question is, how do we do explore exploit for these kind of problems, right? So one extreme Yes, so one extreme formulation is to assume that every user is a separate bandit problem. Right? So if you are a user, I have to choose the best article for you. So every user is a separate bandit, and it's almost like a multi-armed mafia problem instead of a bandit problem. You have to choose the best arm for every single user now, right? And so this is not scalable, as you can see, right? Because many users come to the portal only once or twice. So you just have for many users you only have 1 or 2 samples available for a month, and there is no way you can experiment with 2 samples and figure out what's the best arm for each user.
right? So you have to exploit correlations across users and across arms to solve the curse of dimensionality of the so all the methods we talked about yesterday of figuring out features for users and items and then kind of correlating the CTRs of users and on based on these features become important. And so now the question is, if you're reducing the dimensionality of your problem by using feature-based models, how do you exploit for this class of problems? Right? That's really the issue here. But note that if you are able to reduce the dimension of the problem by using a regression approach, that's a feasible solution to this problem. Right? We started with a very high-dimensional problem where every user is a bandit of its own, and you reduce the dimensionality of the problem by figuring out some commonalities across users and across items using features. Right? So we've already done a lot of work here. The question is, in this reduced dimension space, how would you go about doing the explorers? Right? So here are some heuristics that are used in practice. Again, first of all, I want to mention that calculating a Gittins index for this class of problems is not trivial, and it has not been solved to the best of my knowledge. So it's still an open problem how to come up with a Bayes optimal solution for this class of problems, right? So if you notice, the previous solution which I described yesterday from first principles would not apply directly to this problem, right? Because there we assume that there is a segmentation of users, and for each segment you're counting things, you have a beta binomial distribution. All that will not work when you have models like logistic regression or other generalized linear models. Right? So this is still an open problem, how to compute Gittins index for this class of problems. So in the absence of that, there are some heuristics which are used in practice, and they're pretty effective, right? So first one is the upper confidence bound policy, right? So if you have a model, and if you can compute the posterior mean and some posterior standard deviation, you can just use that as a score for every item, and that's going to induce exploration in your method. Thompson sampling is a very popular method. In fact, it is used quite a bit. Again, the issue here is to compute the posterior distribution so that you can draw from the posterior. So you have to do more work here. Softmax, as I was mentioning, that also applies to this class of problem, and you have to be careful in how you tweak the temperature parameter. And epsilon greedy is always something you can try as a first step. Right? You collect randomized data from a small population and then you do it. Right? So this all applies to the thing. I think the main takeaway here is, from a research perspective, how to come up with a solution that is optimal or close to optimal from a Bayesian set. That still needs to be worked out. There are several papers in this area and again, this is still an active research area, so you can take a look at these papers if you're interested in this area. And you can kind of be up to date on the literature if you really want to work in this area. So far I was describing solution for a single slot. What happens if you have multiple slots on the page? When you load a web page, you have to recommend multiple things at the same time. So how do you generalize the solutions which I described to this problem? And here also there are several heuristics that have been used in the literature. Not a very clean solution still, but again, here is a list of papers which you can read. So in general, heuristics are reasonable in practice. But again, no clear answer in terms of what is the right optimal solution for this class of problems. So anyway, so that was about explore, exploit. Now let's move on to how we would do online modeling. So we talked about feature-based models, which is computing offline components, and we talked about explore, exploit. Now I'm going to talk about the third component, which is once you build your offline model, there are still some parameters that have to be estimated online when a new user or a new item comes in. How do you do that? Okay, so we have looked at this model yesterday. So again, imagine Yij again is the rating that user I gives to item J, and this is a model which we talked about yesterday. So Ui are either features of users, or they are some factors that have been estimated by using matrix factorization and other approaches. Beta J are the coefficients that you have to learn for item J. And if an item is old and has a lot of observations, these are well estimated. When an item comes into the system, the question is how do you estimate or how do you initialize the value of these parameters? And in order to initialize the value of this parameter, you need to have a good estimate of the prior mean for this particular parameter. Right? So the question here is how do you come up with a good estimate of the prior mean so that you can use it to initialize the model when a new item enters into the system, because that's going to help you deal with the false start problem. And there were several approaches. So one is initialize the coefficient based on the item features, right? So this is what we looked at yesterday, right? You have an item, you know the category of the item, you know the phrases in the item, and you can construct bags of features, and that's and you learn the coefficient of these features, and that's how you could initialize an item when it comes into the system, right? So if it's a sports article, then you know it's going to go well with users in San Francisco, for instance, right? So that's about features, but after adjusting for the features, you still have some residual idiosyncrasies which you can capture for a new item, right? So how do you estimate that? And there are several methods of doing that. We talked about yesterday. We talked about how to reduce the dimensionality of this so that you can learn it efficiently online, right? So if you have a 1,000-dimensional user feature vector, you have to learn 1,000 parameters per item when it enters the system. That's going to be computationally expensive. It's going to take time before you can estimate these parameters. So one way is to reduce the dimension of this, project these coefficients to a lower dimensional subspace. And again, this projection matrix is something which you can learn offline by looking at tons of data which you've seen in the past. And then all you are doing at the end of the day is estimating a smaller dimensional parameter online for each item. That helps you convert fast. Okay. Right? And so essentially what we are assuming, if you do that, what you are assuming is your beta j, the item coefficient, is drawn from a prior, which is centered around, of course, the mean that is determined based on the feature, and the covariance matrix, which is not identity anymore. It is given by something called BB transpose. It's a reduced rank model. You reduce the rank of your model, and then that facilitates online learning, faster conversions. And we have, so I'm not going through the details. You can read about that. That was the main idea. And again, we have applied these techniques to several data sets in the past. We applied it to a data set that we derived from MyYahoo. MyYahoo is a particular portal on the Yahoo website where you can customize modules you want to look at. And we are not going through the results, but you can see that if you do the supervised dimensional reduction, which I was talking about in the previous slide, that seems to perform much better than if you do unsupervised dimension reduction. But these are all different dimension reduction methods. So the B matrix which I was talking about, that can be estimated in different ways. Right? You can just take the covariate vectors of items and just do principal component analysis, and that gives you a picture as well. You can use random projection, or you can do the supervised projection which I was talking about. And the supervised tends to work better, of course, because you're using more data than unsupervised. But nevertheless, doing a projection is always a good idea when you have very high dimension. All right, so this is basically to summarize this section. Whenever you have historical data available, so there will be cases where someone launches a brand new product, right? So if someone launches a new module on the website, then you are really starting cold. It's like a cold problem, right? You've never seen this product before. Then you're out of luck because you have no historical data available, and in those circumstances, the only option you have is to look at item features, user features, and learn some coefficients based on those. But if you have a system that is running for a while, even if you don't, you already have a lot of data, past interaction data available to you. So you can use that to come up with better features that you can use to initialize new users and new items. And it's always a good idea to exploit those. Other than the metadata and other features, it's always a good idea to exploit those as well. And that's what we were talking about earlier. Generally, factor models are good because data in recommender systems is extremely sparse. So going beyond a linear model is not always feasible because you end up with high variance estimates. But factorization kind of provides a nice trade-off between linear and nonlinear models. Right? So doing factorization is a good idea. It also helps you score your items at runtime very easily. You're just computing in a product, so the computations are extremely fast. And it also helps you learn things online much more efficiently. So these are nice models. And so we already talked about all that. So great. So now I'm going to move over to evaluation. Right. So we've talked a lot about recommender systems, and now you might be wondering, well, if I'm a practitioner and I create a new method, how am I going to know whether it's going to work well or not? Right? That's a question which is extremely important, right? So how do we do that? So the ideal way to test a new method is to run an online experiment. Okay? You come up with a new algorithm, that's a new recommender problem. You say, okay, well, give me a small fraction of randomized data, which can use my new method to recommend articles, and let's compare it against the status quo, which is currently running on the site. You do an A/B experiment that gives you unbiased estimate of performance. But this is not easy, right? I mean, there could be so many different ideas that so many different people can come up with in a company, especially in companies that are large. So you have to be careful or judicious about running these experiments. Right? If you're running a bad experiment, or if you're running an experiment that provides suboptimal recommendations, you're going to hurt user experience. Right? So there is a cost to running these experiments. There is also an engineering cost to set up these experiments and do data analysis and so on. So you cannot run tons and tons of experiments. You can only run a small number of experiments. So how do you do evaluation offline to weed out some of the bad experiments and only run the good candidates online? Right? That's an important problem. Okay, so for supervised learning, we know how to evaluate predictive auto-sample predictive accuracy. Right? We use methods like AUC, precision recall, log likelihood on test data, and so on and so forth. So those are all well-established metrics. Now the question is, when you are working in recommender problems, do those metrics suffice? Are those metrics reflective of what your performance would be online? And the answer is no, right? Because it's an explore-exploit problem. It's an experimental design problem. I'll give you an example. Suppose you collect data from a recommender problem that only shows 2 articles out of 1,000 to every single user. Okay, so you have starved all the other 998 articles, and that's the data you are collecting. You run a supervised learning algorithm on that data, you are going to get extremely good results out of sample predictive accuracy, right? Because we only have data on 2 articles. So, well, my AUC is 0.9. You launch that model in production, and that model will start serving some of the items which have not been served in the past. And some of these items that you serve would be suboptimal, right? Because they've never evaluated the quality of recommendations or the quality of prediction on these items. You never saw it in the data, so there's no way for you to evaluate, right? And the performance may not be as good as you want. Right? So the data which you collect, the data on which you do offline prediction or offline auto-sample predictive accuracy have to be diverse enough. It has to be representative of your system, right? Otherwise, these metrics will be misleading. Okay? So we need a different metric to evaluate these methods offline. Right? And another thing which I've seen in the recommender systems literature in several papers is whenever we are doing out-of-sample predictive accuracy calculation, I've seen people do random splits of data. Like if you look at Netflix or if you look at movie lens, I mean, particularly this happens for movie lens data. There are many papers that take the data and then do a random split and then do an out-of-sample predictive calculation. That is not correct, because you want your method to predict what's going to happen in the future. You cannot use the data in the future to predict the past. Right? That's wrong. Right? If you're using something like item-item similarity, and if you're using a rating which was in the future to predict what you're going to do in the past, that's not reflective of real-life application. So whenever we're doing offline evaluation, even for supervised learning method, I would recommend you do a time-based split and then do the evaluation. So it's a small thing, but it does make a difference in terms of how you gauge the quality of your methods. Okay? So this was about offline evaluation, and we know that this is not sufficient. So let's go to the online evaluation. And so I was already giving you an intuition of why that's a problem. The supervised learning metrics are a problem. You need to make sure that your test data is diverse enough, representative of the entire system. So what is the best way of collecting data that is representative of your system? By running a randomized experiment. Right? You take a small fraction of traffic and you randomly show articles to users in that traffic, and then use that data to do offline evaluation. Right? You cannot get something which is more representative of the system than that. Right? You're collecting data on all the articles that you have in your system. Okay, so if you have the ability of running a small randomized experiment on your system and collecting data, that data is extremely valuable to evaluate new methods offline. Okay. Right. So here is how it works. Like suppose I'm calling it the random bucket. So random bucket is a small fraction of users who are served recommendations by randomly selecting articles from your iTunes. Right. So your random bucket, and this random bucket provides you with all the logs. Right. So this is the user. This is the article that was served to the user. This is the reward. Right. And again, these are two different kinds of rewards. Right. So this is score 1. CTR, this is like amount of time the user spent on the site after clicking on the article, right? And so once you have this data, now suppose you want to evaluate a new recommendation algorithm X offline, right? For every user visit here, you come up with a recommendation, right? So for every user visit which you have in this offline data, your new algorithm is going to say, hey, this is the best item to serve to that particular user. Let's call it A star, right? If the best recommended article A star is the same as the one that the user clicked, then you get 1 point, right? Okay, well, I am recommending the article which was actually clicked by the user in my randomized log, right? If the best recommended article is something that is different from what the user clicked, then you don't get any reward. Okay? We are pretty much essentially computing the precision at 1 on the randomized log for a new algorithm which you want to test, right? And once you have done that, once you have replayed your data on the historical log which was computed from a randomized experiment, you can now compute how many clicks you got with the new algorithm. If the number of clicks you got from the new algorithm, if the algorithm that gives you the maximum number of matches on the randomized data is the one that's going to perform better in the online exam. So very simple method. The only trick is you have to collect this data from the system once, and then use that to evaluate all the new algorithms which you are going to invent offline. And then out of this, if you invent 100 algorithms and 98 of them have very poor performance on the online metric, on this offline metric, then you don't launch them in production. You just take the 2 which look promising and launch them in production and see what happens. So you can weed out a lot of bad tests efficiently by using this methodology. Okay? This is clear, right? This is very important, right? So you just replay the data and look at the precision at 1. The method that has the highest precision at 1 is the one that is the best. Okay. So mathematically, you can show. I mean, this has been done in this paper by John Lansford and Lee Hong Lee, that this provides you with an unbiased estimate of performance. Mathematically, you have collected data from a recommender algorithm S of X. So S of X is the one that is used to collect data. H of X is what you are evaluating, and you want to compute the expected value of, the expected reward which you get by using algorithm H of X, right? So what is the probability H of X is going to serve item I, and then if it does serve, what is the reward, expected reward you get out of it, right? And you want to do an expectation overall, right? So this is what you want to do, right? And how do you do that? So as I was telling you, right? So figure out all cases where H recommends something that agrees with what S recommends. then what was the reward we got? And alpha t is some importance weight, which we have to compute. And this importance weight is basically, if you have this as an importance weight, then this is going to give you an unbiased estimator of the policy. Right? So if your importance weight is 1 over the conditional probability of S serving I given H served I, then this gives you an unbiased estimator. You can show that very easily. Right? Now, if S of X is a randomized serving scheme, then this conditional probability is the same as unconditional probability. Okay. So if you can collect data from a randomized serving scheme, then this is very easy, and then basically you are just looking at the precision at 1 on the randomized data. So it becomes very simple. If S of X was not randomized, if it was something like a weighted randomization scheme, that's also fine. You can still do that, but your variance is going to increase. Right? Whenever you weighted randomization, your variance is going to be a little higher. As long as you have a weighted randomization scheme that does not serve something in your pool with very low probabilities, you'll still be okay. Right? When you're doing weighted randomization or weighted importance sampling, you have to make sure that none of the weights are very small or very large. That's the trick. Otherwise, the variance blows up. But randomized is the best. But in many cases, you may not have the luxury to run randomized experiment, completely randomized experiment. Like if you have thousands of ads, you cannot do a randomized experiment with thousands of ads. So you may have to do some weighted randomization. However, if you know the weights, then you can still incorporate that into your serving, incorporate that into this formula, and still get an unbiased estimator of what the policy or what the recommended algorithm is going to do on log. So we have been using this very successfully in all our industrial applications, and it helps a lot in weeding out many bad tests. Otherwise, it looks like, well, why should I not be running a lot of tests? There is a cost to running experiments. In a given week today, like at LinkedIn, we run around 20 tests. And if we didn't have this, we would want to run around 100 tests. So there are so many scientists working on the system, and they all have ideas, right? So there will be too many things to test. Moreover, there are many cases where you're running a supervised learning algorithm and you have to tweak a regularization parameter, for instance. So instead of tweaking the regularization parameter by using the supervised learning criteria, you can actually tweak those parameters by using this offline replay method. I was telling you that softmax is very sensitive to the tweaking parameter. How do you tweak that parameter? This is how you do it. You collect some randomized data and then you tweak the parameter based on the replay method. Otherwise, if you have to test 100 different temperature settings, then you run 100 experiments to tweak these parameters online. That's expensive, especially for tweaking the parameters. So this is extremely useful in that sense for tweaking machine learning algorithm parameters or hyperparameters, as we call them. Okay, so that was about the evaluation methodology. And we talked about online learning today. Next, I want to show you an example of how multi-objective optimization works in practice. So I'm not going to go through all different multi-objective optimization one may encounter in practice, because as I said, this is more application specific, but I'm going to show you a particular application. Okay, so again, back to the Yahoo front page example. I'm using it as an example, but the methods apply to all different applications. In fact, we are using it in many different places at LinkedIn as well. So I'm just using it as an example because it's published work, so it's easy for me to talk about it without getting PR approval for things that we're doing today. Okay. So again, we know this example. So back to this example. So the Yahoo Today module, right? Suppose you serve an article. So currently, yesterday we were talking about serving articles to maximize CTR. But just showing links to users that are very easy and then having them go to a landing page where they don't engage much with the site is also not a good idea, right? So you want the users to click and then follow through. Follow through by reading things or by engaging with the site, right? So suppose you serve an article, the CTR of this is 10%, let's say, and we know that after clicking on this, you're going to spend 30 seconds on average on the landing page. There is another article where the CTR is 15%, but you are going to spend 10 seconds. And so now there is a dilemma here. Which one do you show? Do you show the first one or the second one? So the first one, if you maximize CTR, you're going to get a lot of downstream page views to the site, and that may result in better advertising dollars. But if you rank by expected time spent, then maybe you would prefer the first one because the user is going to engage with the site more. And if the users engage with the site more over a long time horizon, they will come back to Yahoo more often, and that would also increase advertising dollar, but maybe not in the near term, maybe in the long term. So how do you make a trade-off in such scenarios? So this is really an example of multi-objective optimization. There could be many such scenarios, right? CTR, time spent, revenue. In the case of LinkedIn, how many people apply for a job versus how many people click on a job. How many people connect with someone, and once they connect with someone, do those people then connect with someone else? So there are many downstream utilities you have to worry about, and that's why this is important. Right? So I'm just showing you exactly the two objectives, but there could be multiple subjects. And here there are three objectives. There is also revenue. Okay, so with that context, here is the problem setup. So you have an article pool. You have k different web properties. Right? So Yahoo Finance is a web property. Yahoo Sports is a web property. Yahoo Entertainment is a web property. Every link you see on the Yahoo front page takes you to one of these properties. So you have k web properties. And that's considered only two objectives: click rates and time spent. Right? And let's say I want to maximize the amount of time users spend on the site, but I don't want to lose more than 5% of the clicks which I would get if I was running a click maximization algorithm. Right? So I can run two algorithms. One is a click maximization algorithm. The main thing there is to maximize the number of clicks, which could mean that you will serve article based on CTRs. But now I say, well, no, I want to maximize. I also want to maximize the amount of time users spend. And in the process, if I lose 5% of the total clicks, which I'm going to get from click maximization algorithm, I'm fine. But I can't lose more than 5%. How do you come up with such objectives? This is something which you have to work with product managers and other business execs who understand the business better and who own the product. They say, oh, this looks reasonable to me. I can live with this. But yeah, if you lose more than 5%, then the total pie, the total downstream traffic reduces, and that's going to hurt our business in the next quarter, so you can't do that. Right? So there is a lot of discussion that goes on behind the scenes to come up with such trade-offs. But given this trade-off, how would you do the sorting is the question which we are trying to answer. At the end of the day, the goal of the analyst is to provide several what-if scenarios to the business decision makers. And then they can look at these what-if scenarios and make a decision. Like based on your data, you might be able to tell them, look, you cannot increase the amount of time users spend by more than 5%, even if you're willing to lose 5% of the clicks. And then they might say, well, this doesn't look like a good trade-off. I'm not going to take it. But if you say, well, you can actually increase 80%, you can actually increase the amount of time users spend on our portal by 80% if you're just willing to lose 5% of the clicks. You say, well, that's a good deal, let's do it. But you need to have an analytical tool to provide them with such what-if scenarios. What is feasible, what is not feasible. And then let them choose the most important thing from a business perspective on the efficient frontier. Okay? So yeah, the first thing is to come up with statistical models and machine learning models that can estimate CTRs and estimate the amount of time you spend on it. That's routine. So we talked about that. Suppose you have done that. Right? So for every user you have a CTR, you have expected time spent, and now you want to come up with a serving plan. Right? What's the probability item J should be served to user I? Right? So I could be either a user, or we can simplify the problem and create different user segments. Right? Either way. That's the serving scheme you need to come up with. Right? And now the question is, how do you come up with the design parameter X? Right? That's the problem. So as I said, the click optimization basically says, okay, Xij is 1, with probability 1, you serve the article that has the maximum CTR, 0 otherwise. Of course, there is some exploration going on. I'm ignoring that for some reason. Okay, so now let's look at this, right? So this is the total number of clicks, right? So Xij is the probability of serving item j to user I. This is the fraction of users in segment I. I'm just doing a segmented analysis. Let's assume there are a few user segments and we want to come up with a serving plan for each user segment, just for simplicity. I'm going to go into the personalized model later on, right? And Pij is the CTR, right? So this gives you the total number of clicks. If you have a serving plan X, which is the unknown you want to compute, this is the total number of clicks you're going to get. Similarly, this is the total time spent you're going to get. You just multiply that with the expected time spent and you get the total time spent, right? So these are the two parameters. And both are linear functions of your design parameters. So you can also add other constraints, linear constraints as well, right? And so, so this is what you want to do. You want to say, well, I want to maximize total time spent on the site, subject to the constraint that the total clicks I get should not be less. I should not lose more than 1 minus alpha % of the total clicks I will get if I have used the click maximization system. And you can also add other constraints. I don't want to lose more than 99. I don't want to lose more than 2% of clicks which I would get on Yahoo Finance if I use the click maximization, because that's the status code. So you can add those constraints as well. Okay. But the key thing is this is a linear program. You can write all of that as a linear program, right? You're optimizing a linear objective subject to linear constraints. Okay. Okay, so the property, you might be wondering, why do you add the property level constraint? Why do you have to worry about Yahoo Finance not losing more than 1% of the total clicks they get? Well, because different properties on Yahoo might have different considerations. If ComScore says that Yahoo Sports might go to second position compared to ESPN next quarter, then they will be very sensitive about the number of page views that goes to Yahoo Sports. And so they might say, well, I'm not willing to lose any clicks at all on Yahoo Sports because it will put us in the second position and our leadership in the sports area is going to go down, right? So there are different considerations why you may not want to lose too many clicks across different Yahoo properties as well, right? So that's why it is customary to add those constraints as well. All right. So, so this is easy to solve, right? You just do a linear program and you get the serving scheme. So for every segment of users, you know what is the optimal serving scheme based on this consideration. You can solve that. Now, instead of using segments, if you go to per user, right? If I say, okay, well, I want a serving scheme like that for every single user. We already talked at length about building personalized models for each user, and now we can't live in a world where these constraints are added at a segment level, right? Because then all the hard work we have done to personalize recommendations based on CTR is going to be lost. So we have to generalize this to the user level, right? So is it straightforward? Well, let's try to look at it, right? So I is the user segment, U is user. Right, so the same formula, but the pi i's of course go away, right? Because now it is at the user level. So total clicks per user, total time spent per user, right? So now you have a variable, serving variable associated for each single user. Okay? And now the question is, does this work? So any guess, will it work? Will the same thing work? If I just move away from user segment to user level, will it work in practice? No? Yes?
No.
Why?
Too sparse.
Okay, too sparse. Anything else? Well, there will be many new users in the system. You can only compute the serving plan for users you have seen in your system. But when you start running it online, you will start seeing a lot of new users. How would you get these serving plans for those new users? That's another complexity. Yes, sparsity is definitely, the number of variables you have in your linear program increases a lot if you have a vector which you have to obtain for every single user. Right? If there are 1,000 articles and million users, we have a billion parameters to estimate from the linear program. That's a very large linear program. It's not very easy to solve that. But the more important thing is when new users come to your site, how do you get the serving plan? You can say, well, I can solve a linear program on the fly. Well, no, you can't solve it in 100 milliseconds. That's the problem. If you had 2 minutes, maybe you can. But if the page doesn't load in 2 minutes, I'm sure you would be the first one to abandon the site, right? So that's another complexity. So you need a way of constructing this plan on the fly by using a cheap estimate online for new users. Yeah, so these are the two main issues. Okay, so the main thing to notice here is if you look at the primal problem, there are millions of variables you have to solve. But if you look at the number of constraints, there aren't too many. You're not going to impose too many constraints, right? You can say, oh, well, Yahoo front page should, you should not lose 5% of total clicks in aggregate. Yahoo Finance should not lose more than 2% clicks. Yahoo Sports should not lose more than 1%. Still a small number of constraints compared to the number of variables you have in the primal formulation. So now can you operate in the dual space? Because if you can operate in the dual space, if you can use the dual variables to construct the primal, then it becomes an easier problem, right? Because the number of dual parameters you will have will be very small given the number of constraints. And so now if a user comes in and if you can just use the dual you can use the dual parameters to construct your primal on the fly by using some cheap formula, then you are in business. Right? So that is the intuition behind the solution. Yeah, but this is only possible if we can convert the dual solution to its primal, and that's not always possible. We know from optimization, you cannot convert a dual to primal for all problems. Especially not for linear programming, because linear programming is a combinatorial problem. Okay, it's not strongly convex. So for a linear program, you cannot construct the primal from the dual. Okay. So what can we do here? Okay, let's see. Well, so use a trick. Say, okay, well, the objective is linear. What I'm going to do now is I'm going to make the objective strongly convex by adding a little bit of convexity to the objective. Okay. So it is almost like adding regularization in supervised learning. Right? So you're saying, well, I want my solution to be close to some serving scheme, and this could be a uniform serving scheme, for instance, right? So Q could be something that says, okay, serve all items at random with equal probability for all users, right? So what this is saying is, well, you solve the linear program, but you make sure that your solution is close to this particular solution. And again, this is the weight you give to this quadratic term, and this is done in many problems in optimization. Like if you're doing something like ADMM, you add that. Adding strong convexity is routine in many optimization problems. And what this does is it converts it into a strongly convex. It adds by adding strong convexity to your objective, you have actually made the problem invertible. You can actually construct the primal from the dual. So you can get the primal for any new user who is on the site through the dual, right? And again, you will have one dual variable for each constraint. So there are not too many constraints, not too many duals. Right? So you do all your offline analysis and construct the dual parameters, and then get the primal back from there. Right? So I'm not going through the math, but you can write down the Lagrange, and you can invoke the KKT conditions. And once you invoke the KKT conditions, this is what the solution looks like, right? So the probability of serving item J to any user U is a function like this, right? And the important thing to note here is this quantity C of Uj, which is a linear combination of the expected time that will be spent by the user plus the click-through rates weighted by some dual mu 0. This is the expected time that would be spent by the user on property k, weighted by some dual mu of k, and then gamma times q of uj. This is the term that is coming from the regularization parameter. Okay. So if gamma goes to 0, then you are kind of converging to the linear program. So as soon as you hit the linear program, then there's a discontinuity. But if gamma goes to 0, then you're kind of getting very close to what you would get out of the linear program. Okay. So this is a small fudge factor. It doesn't. If you keep gamma small, this doesn't play a big role. This is the main takeaway from the entire math which we did. Right? At the end of the day, you're serving articles to user by using a linear combination of expected time spent, expected CTR, and expected time spent on the property. And again, these linear combinations are based on the constraints which you had imposed in the first place. Right? Okay, this makes sense? So if you add 10 more constraints, you will get a linear combination that involves 10 more such quantities. Right? Okay, so this kind of strategy has been used before as well. This is not the first time it has been used. There has been papers in advertising where this has also been used before. And I think the constraints there were different, the objectives were different, but the method or the spirit of the method was similar to what I just described. And as I was telling you, as long as you can predict the probability of a user consuming an article and the expected time spent, you are in business. You can actually come up with a service plan, and that's great, right? Because we've done all the hard work in machine learning to come up with personalized estimate of click-through rates and expected time spent, and now we can use all that with the constraints that have been imposed from a business perspective. So it's a nice situation to be in. So the main thing here is by adding convexity, I have converted that into a QP, and we all know QP is expensive. So while linear programs are much more efficient to solve, it had the problem of not being able to convert things on the fly, right? You can't compute the primal on the fly for every single user. So we converted into a QP. It helped you obtain the primal solution on the fly, but it added the complexity of now computing the dual for millions of variables, right? So that's really, there's no free lunch in life, and as you can see, you solve one problem, but you got into another one, right? Now, how do you scale this QP is the question. Okay. So the way we do this is by subsampling users, right? So when you're solving the QP, even if you have millions of users in our historical data, but in order to compute the dual, these are subsample users. Right? That makes the QP problem more feasible, right? And now the question is, how do you do subsampling, right? So we tried using random sampling of users. We also did some stratified sampling. You stratify the user based on some attributes, based on their affinity to different articles, do some kind of k-means, and we tried both. I'm going to show you the result of what we got by using different kinds of sampling. So these, some of the things I'm talking about have been run in production, some of them have not been run in production, but that doesn't matter because now we have this offline replay metric, which is reflective of what's going to happen in production. So whatever you see here, you should believe this is going to be real, right, because of evaluation methodologies. Yeah. So yeah, Yahoo front page data in 2010 collected, so 2 million page view every day in the data we have. Not actually, Yahoo has much more than 2 million, and we use the replay method. And these are the metrics I'm going to report in the experiments which I'm going to show you. So CTR ratio, right? So this is CTR relative to some baseline. So if I show you 1, that means it's the same as the baseline. If it is 1.1, it's 10% better than baseline, and so on. So time spent ratio, again, relative to some baseline model. That's how the results would be reported. So here are some curves. So these are different Pareto curves, right? So this is real trade-off curve, right? I mean, this is something which you show to the analyst the business owner, and they can actually look at these things and make a decision, right? So you can, for instance, say, okay, well, look at this curve, right? If you lose 5% click compared to a status quo model, you end up getting a 12% bump in the model time spent. You take it, right? So that's the kind of decision making you can force on the business owners by showing these curves. These are all real curves, right? And the kind of Pareto curve you get is important, right? So if you get a Pareto curve that gives you better trade-off, then that's much better than getting a Pareto curve where the trade-offs are not that meaningful or not that attractive, right? So depending on the method you use, you get different kinds of trade-off, right? So if you use the segmented model which I was talking about, where you divide every user into segments, you don't get very good Pareto curve. But if you do things at the personalized level by adding the strong convexity I was talking about, you start getting much better Pareto curves. Again, these are different clusters of users, and as you can see, as the number of clusters increases, things become better. If you go to personalized, it becomes really good. Right. So doing this straight up at the personalized level, even though we have to add some strong convexity to invert the problem, is a good idea, at least to this application. That's what this curve is showing. Here, the trade-off is without adding any property level constraint. So just global trade-off between CTR and time spent. And it's not telling you what these trade-offs are going to do to many downstream problems, right? So that you will see in the next one. Right? So if you add the property level constraint, and as expected, if you add more constraint, then your trade-offs are not as lucrative as they were earlier, right? Because now you're constraining things more. Right? So earlier you were getting a big bump in time spent, now you're going to get a decreased bump in time spent because now you're adding more constraint to the downstream problem. Right? But still, the personalized is much better than the non-personalized. Yeah. So this is showing you. So beta equals to 1. Again, I'm not going through all the details, but let me tell you what beta equals to 1 means. Beta equals to 1 means you maximize time spent, and you can lose 5% clicks, but you cannot lose any click at all for all the downstream properties. Very strong constraint. None of the properties are going to lose any constraint. Beta equals to 0.95 means any given property can lose 5% of its click, which it will get from the statistics. A different kind of constraint, right? And you can see, if you are willing to lose, clicks downstream, then you can get a big bump in time spent for different properties. If you're not willing to lose clicks at all, then you're not going to get the advantage of getting more people spending more time on the property. Right? So again, different kinds of analytical tools, what if scenarios, what makes sense, what doesn't make sense, is very application specific. But at least you have a tool now to kind of visualize all these what if scenarios. Okay. This curve is showing you what happens with different sampling fraction. Like when you're solving the QP with 10% or 20% or 50%. So what this curve is saying is 20% sampling is good enough in our application. If you go beyond 20%, you don't get any more gains, right? So I think all we have to do now is figure out how to scale our methods, QP solving method, for 20% of the random samples we see on the application. Okay, so conclusion. So I just showed you the multi-objective through an example because I think it is such an application-specific thing that talking in the abstract may not make a lot of sense sometimes. So I wanted to go through an example just to kind of give you a flavor of the kind of approaches we can use, right? But what we found from this application is it is possible to increase the amount of time you spend downstream on the properties without losing too many clicks, which is good. Right? You can engage the users more. There are many links which we sometimes show on Yahoo that look very great, like nice pictures and juicy headlines, but you click and then you go to the page. It's not that great. So what this method is doing is it's just eliminating those links to each other. That's all it's So future work, how do you generalize the kind of things I was telling you when you have to recommend things on multiple positions? This was for one position, and what we have been doing so far is taking a more heuristic approach where you solve it separately for each position and just do it that way. But That's not the optimal approach. So how do you write an optimization problem which can handle this for multiple positions and the multiple content on the page? How do you kind of incorporate all that into the same framework? That's a challenging problem. Currently, the constraints which we are adding was only for the next 5 minutes or 10 minutes. Right? You solve the program for this 10 minutes, serve for the next 10 minutes, again resolve it, and another 10 minutes. If I want to add constraints that are more for a bigger if I want to add more long-term horizon constraint, how do you do that? And the third thing which I have not mentioned here at all, but it is extremely important, how does this whole thing interact with explore exploit? Because we had an explore exploit constraint earlier to estimate your PUJs and DUJs, and now you have another set of constraints which is solved through a linear program or a quadratic program. How do you get them all to work together in a more holistic fashion? They're kind of taking a partitioned approach, which I showed you. So I don't know that. Maybe some of this QP program will become a stochastic program, but if it is a stochastic program, then it becomes even more difficult to be solved. So these are all open questions that needs more thought and more research. Okay. So if you're interested in any of these, let me know. We can talk more offline. All right, to summarize, so what I was planning to do is after summarizing this, I'm going to spend the next hour which we have going through a use case study at LinkedIn. Right? So we've talked about a lot of stuff. I'm going to just show you a case study from an advertising application. Hopefully that will give you a good idea of how all the concepts I was describing come together in a real production environment and it starts working impacting the business. But let me summarize before we do that. So the first statement, of course, this crowd will have no problem in grokking, which is, most recommended systems on the web crucially depend on extracting intelligence from massive amounts of data that is collected on a routine basis. That is, of course, at the heart of everything we do. And I think the idea that a lot of data means we don't have to invest in doing sophisticated machine learning is wrong. Because the more data you add, the more heterogeneity gets introduced. And if you really want to truly personalize applications, which we want to, that's how these recommender systems will become better. We need to do good machine learning because the number of parameters increases with sample size for most of these applications. Okay? And extracting the right grouping structure, what group of individuals work with what group of features, that's extremely important. And again, ML has a very important role to play. The fourth point, which is the ability to do continuous and adaptive experiments through explore exploit. That's a key. That's an advantage you have on the web. Right? In many social science problems, you don't have that. Running a survey or running a clinical trial is very expensive. But running an experiment on the web is not that expensive. So that's a very strong, important tool which we have at our disposal when we are working on recommended problems on the web. And how to scale these experiments to take advantage of this capability, that's an important machine learning problem. Multi-objective optimization is often required in real application. Rarely would you see an application where someone is just interested in optimizing for one single objective and nothing else is there. So either you can just live with the heuristics, because whether you like it or not, heuristics will be added. Right? If someone doesn't like something, at the end of the day, there is a product manager who is responsible for the product. And if they don't believe that the user experience is good, heuristics will be added. So you're better off providing them with analytical tools and help them make an informed decision about these trade-offs rather than letting them add heuristics to the system. So then that starts intervening with the machine learning you're doing in non-trivial ways. Okay. So it's a practical consideration. Machine learning practitioners have to work closely with engineering, product, and business execs if you want to be successful. Merely doing machine learning is not going to work. At least today, it's not going to work. Okay, so some challenges. These are a subsample of challenges that we need to work on. This is on the more scoring side of things, right? How do you do more optimal multi-position, multi-page optimization? Right? So instead of just optimizing for one single position and then using a heuristic which says I'm going to just rank independently, how do you come up with a better approach of doing subset selection? Right? So at the end of the day, it's a subset selection problem. It's not an item selection problem. I show you a module with 4 positions. I'm asking you to give me the best combination of 4 items to show for me. What is shown on position 1 may have an impact on position 2. Right? So I think Alex has done some work by using discrete choice models. There's a lot of literature on discrete choice models in the marketing world, and some of that has already been applied, but more work needs to be done to kind of make it better. Right? Explore exploit strategies for large content pool and high dimensional problem. It's still an open problem. We still don't have a Gittins index kind of solution for that. So until that gets solved, it's an open problem. Right? Yes, I'm not saying the heuristics are bad, but there's still more room to grow that. This is something which we didn't talk about today, but how do you use the behavioral traces of user on different parts of your website and come up with a better representation of their tastes? That's an important problem. You have users coming to your site through different channels, right? Some users, there are users who log into both mobile, especially with the mobile world now. For many companies, mobile is now giving a lot more page views than desktop, for instance, right? So you have users visiting the mobile page, downloading mobile apps, consuming content on the iPad, on the desktop. Some of us send you emails as well to consume content. So you have an opportunity of looking at user behavior across these different channels. They visit different properties. How do you combine all that data for different users and come up with a useful behavioral representation for each user that you can use to better personalize? Holistic personalization. We call it, at LinkedIn, we call it holistic personalization. Right? So personalization is not about personalizing a particular page view. Personalization is giving you a personalized experience across the site. It doesn't matter where you go. Whether you go to the mobile page or desktop page, you should have a personalized session experience anywhere you go on the site. And that's only possible if you look at all the traces that the users have left in a more holistic fashion, not kind of do a fragmented approach. And so how do you do that in a better way? That's another interesting question. For instance, you might be exploring the user on mobile and exploiting them on desktop. What's the best way of doing that? Content understanding, I'm not going to belabor this, but there is a lot of work going on in NLP. We are a lot of new research going on in topic models, Chinese restaurant processes, hierarchical VPs. All that is going to become important. This field is going to benefit from all that research. Right? And finally, this is my favorite. I told you when we began yesterday. How do you create machine learning metrics that is more directly correlated to the long-term user engagement on the site? So we can really work very, very hard. There is someone famous in management. I forgot his name now, but I think we often get stuck in heavily optimizing subsystems. Right? So that's not always the right strategy. We should not really go and heavily optimize subsystems. We should try to globally optimize the entire system. Right? So while we are working very hard to come up with better methodology of scoring things, doing better machine learning, we should not lose sight of the fact that at the end of the day, more research that can connect proxies to the real business metric would immensely benefit this area. You can see machine learning having much more profound impact the more we start doing that. So, this needs more work, and we'll see how it goes. As more and more companies start using machine learning systems on a regular basis, I think it is only natural this is going to happen. Okay, so other problems, whole page optimization, incorporating social information for better recommendation. I'm particularly interested in this because now we're working on newsfeed recommendation, where social is a very important component. Right? If you shared an article, then my affinity to that article does not only depend on the content of the article, it also depends on how much I trust your recommendation. So that there's an interesting phenomenon there, if you will. Right? Your affinity to an item is not just dependent on the quality of the item; it also depends on the content producer. It depends on your social strength or social connection with that content producer. So that's quite interesting. So teasing those two things apart is a very interesting problem. And again, multi-context learning utility, I already talked about this. All right, so before I get into the case study, any questions on today's material? Any comments, thoughts? Okay, so let's see how this whole thing works in practice through a case study. So again, I'm going to go through a case study on LinkedIn. So I'm going to talk about the usual computational advertising problem. This is in no way particular to LinkedIn. It is a well-studied problem. Lots of papers written. The main takeaway from here is I'm going to show you something which is running in production. So let's see how things work. Then again, many of the methods I'm going to show you are, from a machine learning perspective, they are trivial. So please bear with me. I think the reason we made them simple was because when you're rolling out stuff in real life production system, there are many other complexities, as I was telling you. So there is an advantage of keeping things simple, at least to begin with. And later on, you can make it better. Okay, so we show ads on LinkedIn. If you go to the LinkedIn page, there are many places we show ads. Right? So here is one example of where we show display ads. Right? This is on the right rail of the LinkedIn homepage. Since last year, we have started showing ads on the news feed as well. So Facebook and Twitter were already doing that. We also started doing it last year. This is extremely important for mobile. So, as I was saying, a large fraction of page views are now shifting to mobile. And what the social networks have found is this is a very good way of monetizing mobile platform. Right? So on mobile, if you open the LinkedIn app or Facebook app, you see your news feed, start injecting contextual ads in between these three, that's a very good way of monetizing. The CTR of these ads are extremely high. Right? So that's what we started doing last year. All right, so let me give you a brief idea, a brief flow diagram of how advertising works. So first, when a user is visiting the site, an ad request comes in to the server, right? And the ad server also gets information about the user's attributes because advertisers target their campaigns by user attributes. There might be advertisers who might say, well, I want to target my ad only to CXOs and above. Because they're only targeting the CEOs of companies. So the ad server is called, and the ad server also gets all the profile information, right? So for instance, okay, well, this is a user who is visiting from the US, age 20, and he's visiting the profile page of LinkedIn, and then there is an ad slot where we're going to show a 300 by 250 ad, right? This is all the information you have to pass to the ad server. As soon as the ad server gets this information, it starts filtering many ads, right? Many ads do not qualify for this particular user because of the targeting attributes that are associated with it. Right? So it starts filtering out. In many cases, there are constraints set by the advertisers. So advertisers might say, I don't want my ad to be shown more than 3 times to the same user. So you also filter them out. There is also something which is called budget pacing that is done in the advertising system. I'm not going to go into it today, but it is an important thing. What that's telling you is if the advertiser has asked you to spend $100, you don't want that to be burned by showing those ads only to people in India. Right? So if you start showing that ad on early morning Pacific time, most of the people that are visiting the site may be from India, and you spend all your $100 just showing ads to people from India, and the advertisers don't like that. Right? Because what that would mean is they have to be really careful in constructing the targeting attributes, and that's not very easy for them. So it's better to kind of space the ad. Right? Don't spend all the money during a particular segment of the day. Just space it out throughout the whole day. Okay, so that's what is called budget pacing. So in many cases, your ads might get filtered out for this campaign because the budget pacing constraints are not met. This ad has already been shown and clicked in this hour by 6 other people, and you already spent $10, so I'm not going to spend more on this. So your ad is inadmissible for this particular case. So that also happens in the system. Once all that has happened, then the ad server has to select the right format to show the ad. Right? So what should the text be? Should the background color be pink or blue? Should the text be written in bold? All the UI issues. So there are several, at least the way we do it is, we have found the UI does matter for advertising. Right? So there are several UIs that are created by our web devs every week. And we also run an exploit algorithm on that to figure out what is the best UI to show to different user segments. So I'm not going to talk about that, but behind the scenes there is an exploit algorithm running to select the right format for each user. Right? So that's the first thing we do. We select the right ad format for this particular user. Maybe it's a pink background with bold headings, or blue background with italics, headings in italics, those things matter. Right? Okay, so that's done. And then it goes to the response prediction engine, right? So, okay, I've selected the format, I know the set of eligible ads, now I have to rank order them and run an auction, right? So, in order to rank the ads, you need to compute the response rates, or the CTRs, conversion rates, whatever your metrics are, right? So that is where the response prediction engine comes in. That's where all the CTR estimation and stuff we talked about, explore, that's all happening there. So once you send the ads to the response prediction engine, it gives you the estimated CTR, and you multiply it by the bid. So bid is the amount of money the advertiser is willing to pay if his ad is shown to this user and clicked. Okay, I'm going to pay $2 per click, and I'm going to pay $4 per click. These are, when you're setting up your ad campaigns in the UI, you mention how much you are willing to bid. It's very easy for you to run an ad. Like I ran my ad on LinkedIn. I was running an ad to send users to a website where I had a tutorial, ICML tutorial a few years ago. I think with $100 I got 40 clicks, so not bad. It's very easy for you. If you want to advertise something, very easy for you to set up an ad on it. Do that. You get nice statistics. Facebook also the same. Right. Okay. So you sort it by bid times CTR, right? And so this is a 300 by 250 slot on the profile page of LinkedIn, and this format which we selected allows you to place 3 ads. There are some formats that allows you to place 2 ads. There are some formats that allows you to place 1 ad. So that's why I was talking about automatic format selection. So it allows you to place 3 ads. You rank order the top 3 ads and you placed it there. Okay, and again, this is all happening within 100 milliseconds. So it's important to know that this whole thing is 100 milliseconds. Right, and then if the user does not click, I'm just assuming all advertisers are running CPC campaigns, which means you only pay if someone clicks. There are some other kinds of campaigns as well, like CPM campaigns, but let's ignore that for a moment because that's not very important for this tutorial. So if a user clicks on it, then the advertiser pays, and the advertiser pays by using what is called a second price option. What the second price option does is if there is a click, the advertiser pays the minimum amount that is required for that advertiser to win the auction. So this advertiser pays this because this is the minimum amount the advertiser had to bid to win the auction. The advertiser might have bid $2, but this might be 1.5, right? So he pays 1.5 because this is the minimum amount he would have had to pay to win this auction, given the competition. Okay, so there is a nice economic theory around this, why this is important, why this leads to truthful options, and so on and so forth. Not very important. Think of this as an utility computation component of this recommendation system. Right? But you can read more about this if you're really interested. Very fascinating stuff from economics perspective. All right. So now the crux of the problem from a machine learning perspective is to how do we do the response prediction or the CTR prediction as we were talking about throughout the lecture. As I said, the machine learning here would be trivial. Nothing surprising, but let's go through it. So what are the feature vectors we have here? So at LinkedIn we call users members, right? So you have user feature vectors. So some of these feature vectors are derived from the identity of the user. So all the information you have on the LinkedIn profile, like which industry you are working in now, which industry you worked in before, what is your title, what is your seniority, which geolocation are you coming from, education, all these things are in your profile. So we use all that. We also use all your behavioral attributes, right? What have you been reading? What jobs have you been clicking on? And what articles are you reading? What influencers are you following? Who are your friends? What are they reading? All that stuff. Right? So that's all behavioral attribute, network attribute. And then for every ad, we also can extract some features, right? So what is the ad about? In many cases, it is members or users like me who run the ads. So if I am the one who's running the ad, you know who is the member who's running the ad, and you know everything about me, so you can use features of ads based on the originator, the advertiser itself, the text of the ad. You can run LDA topics and get some topical vectors as well. Context feature, are you running the ad on the jobs page, on the search page, on the profile page, so on and so forth. Is it on mobile device? Is it on desktop device? Those kind of things, right? Okay. Oh, sorry, there is a typo here. The T here is going to be K. I think there's a typo. It should be K, right? So this is the response when ad J is shown to user I in context K. So either this is a T. So I guess let's make it a T because that's easier rather than making it K. Okay. So this is a T. Okay. Context is T. Okay. So the usual logistic regression, the response follows the Bernoulli model, and the Bernoulli model has a log R's, and now the log R's is composed of two components. The cold start component. So this component is purely a function of user and item features, as we were talking about yesterday. Right? So based on all the profile features you know about the user, based on all the features you have about the ad, what is the best way you can estimate the affinity of that user to this particular ad? Think of San Francisco users' affinity to baseball. Those are the kind of things that are captured. And then the warm start are the residual idiosyncrasies that are not captured by this component, right? So these are per user models, right? So per ad model, right? So this is the affinity. This is the global popularity of the ad, the residual global popularity of the ad. This is the affinity of the ad to this particular user with features xi. This is the affinity of the ad for this particular context, DFT. We are not personalizing per user because ad data is extremely small, so you don't get too many clicks. So if you look at any particular user, the number of clicks that are done by a user is very small. So there is no point in personalizing at the user level for advertising, not for other applications, just for advertising. Right? So we are only personalizing at the per ad level, not at the per user level. For simplicity, because it doesn't buy you anything. It just adds more computation without doing more stuff. Okay, so the usual cold start and warm start. Right? This is the online component, this is rather near online component, this is the offline component. Right? That's what we talked about on the lecture. And these are the parameters you have to estimate for the cold start. So these are stable parameters which don't change too much over time. So you can update them once a day and it will be fine. These warm start parameters are the ones that change rapidly. So whenever, so you have to update these ad-centric parameters every few minutes or every few hours at least. In our case, we have found updating them every few hours is good enough because, as I said, the number of clicks you get in an advertising application is not that high. Right? So you can wait for a while before you update this model. So these are all near real-time applications, and all these parameters are the L2 penalties. We also have tried with L1 penalty. The results are similar, but the model is more sparse, so it helps in expediting the online computation. The SLAs of 100 milliseconds are met more easily, which is a good thing. But I'm going to just assume for now it's L2 penalty. You can also do it with L1. Okay. Okay, so now I'm going to talk about model fitting. So single machine, we all know how to do it. Model training with large-scale data is also pretty much becoming a commodity nowadays. So not too much innovation here, but I'm going to still describe how we do it for the sake of completeness. So the cold start component, actually, we just do it every week. We started doing it every day, and then we moved to every week, the cold start component. It didn't make a lot of a difference. So we just saved computational effort and just stopped doing it per week rather than per day. The warm start component, as I said, is more dynamic. And I think the latest is we update it every 3 or 4 hours right now. That's good enough for this. Okay. So this is done every week by running a large-scale logistic regression on large amounts of data. This is something which we can do by running a per-item logistic regression. Okay. Why is that so? So let's go back to the previous slide. If this component is known, and let's say you only want to update this component, then each parameter over here is associated with a particular ad, right? So you can just split the data by ad ID and run a separate logistic regression for each ad ID. It's a very simple divide and conquer computation, right? So, and this is done every 2 or 3 hours, right? So not too many parameters. The warm start doesn't have too many parameters. So you can just run for item logistic regression, it scales very well. All right? Okay, so how do you do explore exploit? So since the cold start components are estimated by using tons and tons of data, we assume that the variance of these estimates are very low, almost close to 0. So there is no need to do exploration there. I mean, if you do Thompson sampling from a peak posterior, you'll always get the mean estimate most of the time. So you don't do anything there. On the warm start component, the estimates have much higher variance, right? Because the ads might be very new. You had only 5 clicks on the ad. You didn't learn the warm start parameter for that ad very well. Because the posterior is not peaked, spread out, so you want to do some explore exploit there. So there we do Thompson sampling. So because this is a very easy heuristic to implement in practice, right? You draw a sample from the posterior of the warm start component, right? And that's how it is done. So let me show you the results. This is the results I'm showing you from live traffic, which was from last year. Now the models I'm showing you are now 100% unlinked, so there is no experiments going on. We are running different variations of the logistic regression I'm showing you, but the logistic regression is now 100%. So control. So this is the control model that was running on the LinkedIn platform a year ago. Cold only. So this is a model which only includes the cold start parameters. It does not include the warm start parameters at all, right? So the only way you estimate the CTR is by looking at the affinity of users to an ad based on the features alone. You're not doing any per ad adjustments for the warm start. So laser, that's the name of the new model again. I don't know why we called it laser, but the name has stuck around. Actually, we first started calling it loser. And then our CEO said, no, that's not good to you. Okay, what can we do? Okay, make it laser. So now it's laser. So this includes the cold start and warm start. And laser E is, it includes cold start, warm start with Thompson sample. Okay, so I'm going to show you some metrics here. Three models. So this is an experiment, as I said, was running last year. So control is 10%, laser exploit is 5%, and the laser is 85%. So this is another way we found that you can run like epsilon greedy, but this is not quite epsilon greedy. Right? On 5% of the traffic, you're actually doing exploration using Thompson's sampling, and on the remaining 85%, you're not doing any exploration. You're just selecting the most popular based on the laser model. So you don't always have to do epsilon greedy in that 5% or 10%. You can actually have some clever exploration strategy running in a small fraction of your traffic, and in the remaining, you can just select the most popular, whatever is the most popular. So that's what we had tried different variations. Like we would change the explore exploit fraction to 50%, 40%, and I'll tell you what happens if you do that. You can play around with explore exploit that way as well. You don't have to run explore exploit 100% all the time. Sometimes not necessary at all. We just have enough exploration, maybe 5 or 10%. Okay, so I think the PR guys took out the numbers. Yeah, these are all positive, nice numbers, but I think they probably took it out. Okay. So, but it's all nice numbers. Maybe because it's revenue, so I guess. Okay. So I'm just showing you the result from the online bucket test for 7 days, and the thing I wanted to emphasize here is both these models are uniformly better than the control model. Right? And from statistical theory, we know these. It means that the control model was an inadmissible estimator, right? So that's what I wanted to stress. It's not up or down; it's uniformly better. Same for the revenue as well. The revenue was also uniformly better. Okay, so insights, there is no insight. So the only thing I want to emphasize here is if you look at the model without exploration and with exploration, the performance was similar. And so that was a bit surprising to me because what I was expecting was if you're doing exploration, there will be some cost to the exploration. But it seems like the features we had were good enough to provide good estimates of the affinity, and whatever residual variance we had was not that much, right? So the exploration cost was low. And again, there are some slides which I have removed here, but if you look at the data analysis for the exploration bucket and the non-exploration bucket, you can clearly see that for new ads, you do a lot of exploration. So that everything was in the right direction. But what happened was the exploration bucket was doing a lot of exploration for the new ads, but it was really picking up very good ads very quickly. So that kind of mitigated the cost. In general, you don't expect that. In general, if there is an explore bucket, you tend to see lower metrics compared to the explore bucket. But in this case, that didn't happen. The other good thing, so this is a nice story, right? So if you looked at the explore bucket, we also looked at how much. So we're looking at diversity metrics. Like, okay, let me see how many ads is a typical user exposed to. It's a good metric, right? So if all other metrics remain the same, and if a particular algorithm exposes a user to more ads, then it's good user experience. So the exploration bucket was exposing every user to 8% more ads on average, which is great, right? That means we are kind of spreading out the campaigns for each user and yet getting the same metric. So the exploration, although it does have machine learning advantages, in this case, it also had user experience advantages, which was pretty nice too. And in fact, we also work very close with the account managers who are working with the clients. And whenever a client puts a new ad, they kind of expect something to happen to their campaign. There were complaints in the past. Well, I'm running an ad campaign for 2 days, I see nothing. Oh wow, I should not really advertise with LinkedIn because nothing happens to my campaign for 2 days. So this exploration also improved that. Whenever someone put a new ad, it will kind of give them something and they can see some action happening on their ad. So due to that, we actually ramped up the explore exploit to a very large fraction. Not because of machine learning, but because of the other side effects, which is quite interesting. Okay.
Excuse me.
Yeah.
Why is showing more ads a better user experience?
So if you are a user, you don't want to see the same ad twice, right?
I'd rather see no ads.
Well, Okay, unfortunately, there aren't all users on the web are not like you, because otherwise the advertising industry would be dead, right? And if that industry is dead, you will have no free content on the web. So most users don't like ads, and that's actually me. So that's our problem. We have to make it better by doing better machine learning. I go to Google. Google doesn't know I'm a vegetarian. It shows me restaurants, steakhouse, and all. So. And that makes me feel, well, there's so much to do in machine learning, right? There's so many machine learners at Google, and they don't know I'm a vegetarian. So, and I think I've given them enough ample traces to figure it out. So imagine a world where the ads are as relevant as all the other content you consume. Would you not click on ads? So you're saying the ads are not clickable because they're not relevant. That's the only reason why you not click on it. But if you get what you really need,
I just doubt that more campaign ads is better.
more, sorry?
I just doubt is that your laser E, because it serves significantly more ads, that this is better.
So not more ads. What I'm saying is among the ads that are served, there is more diversity. So 8% new ads. So if you take a typical user in the non-exploration bucket and the exploration bucket, the average number of ads they see is the same, but the diversity is more. So you see more variety of ads. And the click rates are not changing. The revenue is not changing. So if you are going to the site and the site is changing more often, you are seeing more new things, then probably it's better user experience. Again, this is just an intuition. I probably don't know. I mean, if you really want to get a good answer to that, then you have to do user experience studies. You have to get focus groups sitting in a room, saying, okay, let's do. Okay, you are getting laser EE, you are getting laser. Tell me what is going on. So we've not done a rigorous study like that, but this is more intuition. Everything else is the same. You're seeing more variety. Probably that's better. But yeah, I agree. It's not rigorous. Yeah, can make it better. All right. Okay, so I'll spend a few more minutes just talking about the practicalities of issues here. So again, a lot of engineering issues that have to come together to make these things work. As we were talking about yesterday, right? Showing you a big chart of the different flows, engineering flows, and how machine learning interacts. So those are important, right? So so I think this, I want to emphasize this. I mean, these things are all machine learning, but good tools, right? So building good engineering tools is extremely important, right? So, you know, writing programs that could be reused for doing feature extraction on a routine basis, very high performance inference engine for deployment. Otherwise, you will not get 80 milliseconds. So, you know, we have to do a lot of innovation on the system side. You know, we have to cache results, partial caching. Like if you have logistic regression, there are different components. You know, you make asynchronous calls. Sometimes some of the components are not available. If they're not available, we just use the previous estimate and kind of do things that way. So a lot of systems optimization. I can go into the detail offline if you're interested. What that helps us do is people who are really focused on modeling and machine learning, they can really focus on the model without really worrying about all these other things. Right? You know, building a set of libraries that is very easy to use is important. And this is true for most big companies. When we started the project, there were a lot of things to be done. So we spent a lot of time building those reusable components and tools that can help us launch these models very easily in a more routine basis. Because if there are no tools, you'll spend a lot of time building a model. Often you will make a lot of errors. And what happens is, at the end of the day, you know, all the A/B testing that happens in web companies is a human gradient descent. So the better tools you have, the better gradient descent you have. So that's why it's important. Okay, so yeah, this summary is more particular to this application, so I don't want to get too deep into that. But I do want to emphasize, since this is more of an academic crowd, many of you are already familiar with these things because we have already had stints in the industry. But for those of you who are not familiar, some assumptions. If you're taking a first course in machine learning, there are some assumptions made. I'm not denigrating these things. These are very important. If you don't have a good foundation, you cannot do more complex things. Right? So it's important, but it's also important to keep in mind that don't expect that if you go to the real world, everything will apply. You just have to be ready for a change. But whatever you learn here and whatever the foundation you have here is going to help you reason about things. The best thing about having a foundation is it tells you what not to do. So if I think about it, well, if I didn't have a formal education in machine learning and statistics, what would I lose? I would not know what not to do. That's what I think foundations do to you. There are so many different ideas which you will knock off right from the very beginning. You will not experiment with those. And that helps a lot because then your gradient descent is faster, right? You have meeting graphs. Okay. So data is not stationary in practice. Features, items change constantly. Training data is clean. That is not going to happen. No matter where you go, some places that we all suck. Some suck less than others. But training data is not good. There are a lot of issues. Right? Frauds, tracking delays, and these things are routine, and you just have to embrace it as part of your life. You get better over time. It's not there. Training is hard, and testing and inference. Yeah, so we put a lot of emphasis on training models. Often we are not worried about inference, like computing these things, but as I was telling you, computation at runtime is extremely important. So you have to think about it more holistic way. There is no point in building something which cannot be computed. If you want to build something that can be computed, so you have to think about that. And, yeah, models don't change all this. It's all the time, right? Complex algorithms. So I may get into trouble here, but take it for what it's worth. Okay. So my views are also changing. Okay? So this is the view I had 2 years ago. Now I'm more ambitious, so maybe that's not true anymore. I think we can go for complex algorithms. If you have a good system and you want to squeeze more out of it, and you have laid a good foundation, then yeah, why not? Go for the complex algorithm. But do the easy things first. Don't go for the most complex algorithm in the first place. Right? Try the most popular, try simple stuff, build your baseline. Because those baselines helps you debug your complex model. If something goes wrong in your complex model and you don't have a baseline, it's very hard for you to isolate the problem. The most important thing in these systems is to be able to isolate the problem. If something is wrong, in many cases I've found there was nothing wrong with the models. There was something in the serving system that was broken. How do you know what is broken? So in many cases the offline replay has helped us a lot. So if I do an offline replay with a model and the performance is great, and suddenly the online performance is rather poor, there is a very high probability that something in the serving pipeline is broken, not in the model. But if you find that the offline replay itself is bad, then maybe something is wrong with the model. So building up a stack of models from simple to complex is a good thing because it helps you understand the system better. Every model is a null hypothesis. You're making an assumption about the system, you're running a null hypothesis, and you find that there's a deviation, and that tells you about the system, right? That helps you learn about the system. You're hypothesizing, you're looking at the deviations, you're learning about the system, you iterate. And yeah, if you can build up a stack of models from simple to complex, why not? Just do it. Okay, so I think probably we have to end at 11. So before I go into this, I'll stop and see if we have more questions or more discussions to do. I'll leave this here, but let's see if we have questions. I think we should also give the next speaker time to set up. So, but I'm open to questions or comments. Anything that's on your mind. Nothing? Everything's crystal clear? High crowd, huh?
I have a question. So when you compare the optimizing CTR and time span for the segments or the properties, and then you move to personalization, and then would it make sense to learn on segments and then use that as a prior for the instead of this Q regularizer term that is for personalized?
Yeah, that's a good thought. I think we have not tried that. So the question was, we had a serving scheme per user that I was denoting with XUJ, and then there was a serving scheme per segment which we were denoting it as XIJ. So Sergey's question is, why don't you learn the XIJs and then use it as a prior when you're estimating XUJ? For instance, the Q which I had in the convex penalty could be an XIJ, right? So you can regularize the XUJ by shrinking them towards XIJ instead of Q.
Right.
So we have not tried that. I think that's a good idea. If I get to work on a problem like this at LinkedIn, I'll try that. But unfortunately, I don't have access to the Yahoo data anymore. Any other questions? What's on people's mind? Nothing? Yeah.
So a simple question. So if the user uses a mobile device, is GPS location as one of the features?
So when you are signing up for the app,
Yeah.
we ask you to opt in. If you opt in, that is available for most apps now. Most users would sign up for it because it gives you good information. In some cases, we also serve ads, and if you are like him who doesn't like ads, then that's a problem. But otherwise, it's okay. Okay, any other questions from yesterday, today? Comments? Oh, there is a question? Yeah.
I had a question about your point about simple versus complex model. So let's say you want to build another complex model which requires some more data, some more correlated data that you have not yet collected, and that model will help generate more related data that will kind of feed into the model and make it better. How do you deal with a problem like that? Like how do you run that model which is going to not do that well in production initially, but over time is going to improve?
Okay.
Have you ever faced with a situation like that?
Oh yeah, we face it all the time. Yeah, so let me give you an example. So for instance, suppose we did a recommendation on desktop. Right? We didn't launch it on the mobile platform. Right? And now, we found good results on desktop, and now we want to launch something on mobile. Right? The mobile, we don't have any, well, let's assume for the sake of simplicity, the mobile did not have that kind of app before. So they have launched a new jobs app, which was currently not there. And you still have to show recommendations, right? So that's the cold start problem I was talking about, right? So how would you do that? So in general, what we have found is in a situation like that, if you have a model that is on desktop, you can start serving recommendations based on that data, right? And then you start running some exploration bucket in the mobile platform. You start collecting data from that platform, and then you first gauge if those recommendations are correlated in any sense at all to the desktop or not. Right? In many cases, they are correlated, and then you can combine these two data sets to build a better model. In other cases, you may find that that platform has a totally different interaction, and then you have to build a separate model there. In general, it is, in the case of this example, desktop and mobile behaviors are correlated because there are many users who visit both these things. But I can imagine situations where you just have no data at all, and in those cases, you have to go by semantic similarity kind of methods. Right? Okay, oh, this user and this is what I know about the item, and semantically they are reasonable. So out of all the items I have, I'm going to retrieve the top K that are semantically similar in some sense, and then do some explore of that. But again, there is no silver bullet there's no silver bullet answer to the question you asked. It has to be, in many cases, it is more about setting expectations with your partners. So if you clearly articulate what the issues are, your product partners, your business partners, and clearly tell them what to expect and how you are going to iterate over time, they get it. I think that's the best way to proceed. Because if you don't do anything, they will run something based on heuristics. They will say, oh, okay, for this kind of users who have subscribed to this particular channel, like Harvard Business Review, show this article, otherwise don't show this, right? So whether you like it or not, they will still do their own machine learning, which is based on gut feeling. And they are open to ideas like this, so it's better to just work with them and do a combination of both. In many cases, what they say makes sense, right? And, you don't want to show something to a completely unrelated population. So it's a combination, I would say.
Oh, yeah. You mentioned that social information can be used to construct features.
I'm sorry.
You mentioned that social information can be used to construct features, especially I guess for this platform. Can you give an example?
Yeah. So, for instance, if you look at people recommendation, the number of common friends is a very important feature. If you look at feed recommendation, then the number of friends who liked an article is an important feature as well. And there are many such examples, right? So what your network does have an impact on what you like. Or in many cases, it's not about what your network liked. There are some selected group of people in your network, who you like to follow, right? So for instance, in my network, my CEO liked an article, I typically like it. Not because I'm sucking up, but he shares good articles.
Yeah. In order objective you want to optimize, I guess you mentioned like CTR and the time users spend, and also you mentioned like the long-term objectives. But I think all the objectives are from the company side or from the business side. But have you ever considered about like from the user side? Maybe users' intention or maybe users' need, what they need, and based on what they need and what their intention, to recommend things for them?
So I think most of the objectives are from the user side, except in advertising maybe a little bit, but in general, all good companies always optimize from user side. User experience is the primary objective. So when I'm talking about long-term, it is more about long-term user experience. Right? So if I show you ads that are not good, and I'm going to get a lot of money just because someone is willing to pay, but I start showing you bad ads, that's not good for the health of the network. And yes, I can make money in the next month. But many of these users will be annoyed and they will not come to the site. So in most cases, we always optimize for user experience. That is the primary metric. In an ideal world, if the company is in a hyper-growth stage, you don't have to do multi-objective because the pie keeps growing. Right? Whatever you do, if the whole pie grows by 200%, everything grows. Right? So nobody cares about multi-objective in those scenarios in general. The company becomes big and the growth slows down, then there is often some zero-sum objective. And there too, member experience is the most important. If you look at web companies, some companies survive for 15 years, some survive for 20, some survive for 50, some survive for 5 months. It all depends on who optimizes for member experience. Companies who don't optimize for member experience do not survive for that. At the end of the day, that is, if you have users coming to your site, the business is going to be there. If the users stop coming to the site, you're out of business. So all these objectives are for users, right? So that's why CTR cannot be the primary objective. Because you can always show easy links with nice pictures, when you click on them, you go to a page, nothing, right? It's bad user experience. You're always thinking about user experience. Users are very unforgiving in this case. If you piss them off once, they never come back. Think about yourself. Will you go to a site if you have an experience like that? Because there's so many other options.
Yeah, because I guess the CTR and other stuff is indirectly measures user experience. But have you ever considered like directly to use like user's intention as objective?
Yeah, so that is the problem I was talking about, like how to come up with a better proxy that measures users' experience. It is to the best of my knowledge, there is no coherent solution to that. Companies do things like focus group studies. If you launch a new model, there will be some focus group of people who will look at recommendation A, recommendation B, and provide you with labels. In web search, it is done very routinely, right? You have editorial labels for a query. So there you have the query to anchor your editorial label. We do crowdsourcing. And I think one of the exciting areas, to your point, is what you can do in machine learning is how do you collect all the explicit user labels you have? How do you collect all the implicit labels like links and other things, and how do you combine them together to come up with a better user experience metric? That actually is a very nice problem. I don't know. Does someone know some work done in that area? I'm not aware of it, but yeah, there may be some papers along there. And I think that's a very important. That's a very interesting area. Like how do you combine explicit labels and implicit labels? If you just do the usual likelihood-based approach, there is a danger because the amount of implicit labels you have is so much large. The likelihood will be overwhelmed by those labels. The small explicit labels you have may not have much of an impact. So you need some different methods to achieve a balance. But at the end of the day, the crux of the problem is what is the right metric, right? You don't know what is the right metric and what is the metric that correlates with user experience in the long run, right? That's the problem I was talking about. Like, there's a gap in that research today. We are very good at optimizing the proxies which are already constructed, but we're not that good at constructing new proxies that are more reflective of performance. Okay, so I think thank you all. With that, I'll stop and with the next speaker. You can take a 5-minute break probably.
I'm sorry. There are some political issues, but anyway.
So we can also talk about
Oh no, it's one of those build connectors. Oh, no, actually it's an idea. Another one of them is physics.
Go to the restroom.
Yeah, to get like beyond the 2 hours, it's 16
Really?
Yeah.
So you have days of processing. It never.
No, I just thought.
That's too bad. That was like 2 hours and like 2 minutes.
Yeah, 2 hours and 2 minutes.
We'll just chop off the ends in the beginning.
Yeah, I'll probably do something. No, that's fine. That's where there's some factoration. Yeah, that's work, but it might not be. Actually, it's pretty.
Need water or anything? Water.
Yeah, that's kind of thing. Yeah, actually, days. Well, yeah.
How was
Oh, okay. So it's just
Okay, so may
may I encourage everybody to take a seat again because we're starting.
Is the video starting again?
Well, not yet. Actually, I need to read you out. Okay. So this is for the camera. Get it on. And this is for amplification. Yeah. So this is amplifier. No. Are you on?
You're on.
So it's a great pleasure to have Dan Feldman here. So he'll be telling us a lot of really nice and amazingly useful things about core sets. So those of you who haven't heard about core sets yet, well, I think this is really mandatory listening. So he is in between several institutes right now, just moving from the MIT, where he's a postdoc, to the University of Haifa. And yeah, it's a great pleasure to have him here and tell us everything about core sets. And a lot of applications, and they're much more widespread than you can ever think. Okay. Thank you.
Thank you guys for inviting me, also for the other organizers. It seems like a great workshop to be in. And since I have much more time, I can tell you more about the real stuff that's important, not just tell you my results that you doing for my friends. And I'll start a bit with my background and how I got to the course at regime. So when I was a graduate student, I worked with several startups in the around 2000, for the Power Code. And I worked with a company that tried to do personalized coupons. So for credit card companies, or for other type of supermarket, we try to give the right coupons for each person. And I tried to improve the classifiers of the company. And one of the things that happened to me, and maybe happened to you, every day I had another idea how to improve things. You spend a few weeks to implement this, and it looks like a great idea, but nothing worked. You spend another 2 weeks and nothing works. So I decided to start off with academic papers, to download papers, show how to solve the problem, and it looked amazing in the paper. They show how the results significantly improved compared to the state of the art, and they convinced my boss to give me a month to implement this kind of papers. And again, it never worked on my data. Always work on the paper, on their data. And I think in image percent, they used to say that to get a master, you need to show the algorithm work on 5 images, and in PhD, it's 10 images or something like this. It was really frustrating. So that's why I decided to start with a more theoretical algorithm that have provable guarantee that the algorithm will also work on my data and on your data, not just on the papers, which is much harder, but then we have some guarantees, and there's less probability that we'll get nothing. So in the company, we tried to, one of the tools that we used was the decision trees. So we take the data, and instead of computing one decision tree, which is a well-known classifier, I hope that you already know it, we try to separate the data to several subsets. We compute decision tree for each different subset. And then the final classification was based on the result, like majority vote, of all these classifiers. So an ensemble classifiers is called like these, take a lot of small classifiers on different data sets and try to combine the result, like several weak classifiers, several judges try to decide together, not just one model or judge. And the question that I try to think about is how to partition the data to get the optimal solution. Instead of just random separate the data, partition the data into points, let's try to do smart partitioning. So I went to my supervisor on Sphere, and we tried to prove things and realized that even for one decision tree, no one understands how exactly it works. It's mainly about heuristics. So we moved to neural networks, and it was even worse. And then Professor Fiat suggested me to reduce the problem. Every meeting, let's take just 2 decision trees. Okay, don't work. Let's like two small classifier, 2 supervised vector machines. Until then, eventually we just come, we just reach this problem. We have endpoints on the plane. Just classify them by 2 lines. So 2-dimensional space, you have endpoints approximated by 2 lines, say that the sum of square distances will be minimum. I said, come on, I just came out from computer vision. They do faces recognition in high-dimensional spaces and all this stuff and big data outliers. What's 2 lines? I mean, come on. I said, okay, so give me how to solve it. And it turned out there is no algorithm to solve this problem with provable result. And I'm talking now 2-dimensional space, small data, nothing. So eventually this was my master thesis. And when I started my PhD thesis, I tried to have more algorithms that would work on what we call today big data, and that would be much faster, almost linear time. The previous algorithm was too theoretical. I read a paper by Matushek. It's called K-mean clustering. And it was the first provable algorithm for K-means clustering that ran in near linear time. But actually, it was n multiplied by log n, some exponential for something huge, k over epsilon or something. And it was about, I think the full version is probably about 100 pages, but the original paper was about 40 pages. And you can find every technique in computational geometry you can find in this paper. It was really highly theoretical paper with a lot of techniques that are totally impractical, very hard to implement. And the result was also, I mean, it was n multiplied by something, but this something was quite huge. It had all the problems that people complain about theoretical algorithms. And I spent a year about learning this paper. And I'm very happy about this, by the way, because this when I learned all the classic techniques, I learned the language that I use today. And a lot of people do the mistake that try to print millions of papers from the web, and every day convince them that you read 10 papers. It's much, much better to take 1 paper, spend a month on 1 good paper, and then continue. And you see that actually all the other 100 papers are just small variation usually. For most of the techniques that me and also I see my friends use, there's some main important ideas that are very hard to understand and solve. But once you understand them, it's very easy to read all the other related papers. But if you just read, it's a bit like, you know, when we learn for an exam, there are a lot of people that just, today I read the notebook. You just go over the page and move your head, but you actually didn't learn nothing. You need to solve exercise and need to make sure that you understand every proof. And so I spent a year in this until my supervisor said that I won't get a PhD just because I understood this complicated paper. And then it was talked to 2004. It was a paper by Sarella R. called and Matsundar, and it's called Courses for K-mean Clustering. And after 3 pages, we show how to solve the K-means problem. One was epsilon provable approximation. And all you need for reading this paper is a multiplication table. It really was a simple technique, nothing sophisticated, 10 lines in MATLAB, and that's all. And that's when I fell in love with the Corset idea. And the rest of my PhD was to generalize this result for lines. And actually, we have the first Fox paper. It was also very hard because everyone was very pessimistic. Actually, Sarella Ped himself come to visit me and say that just thinking a lot about it, this is probably impossible to have Corset for my problem. But eventually, I found this Corset and we polished it. And since then, I just keep making more courses for other problems. And in this few lecture, I try to explain what is the magic of the Corsets, how we use it in practical application, like in the robotics lab in MIT now, how I use it in the industry, political issue, academic issues, and papers. Today it will be more like hand-waving and the main ideas, but in the next lectures we'll get more into the math and the proofs. I hope not too much math, but just give you the main ideas. So, what is the main idea behind Corset? So, roughly speaking, give me data D and have an algorithm A. So, Corset is problem dependent. It's for a specific algorithm. And it's very hard to compute A to D. You want to run an algorithm on the data, but it's take 2 to the n, even for small data. Or it's take n squared, but it's too much. We need near linear time algorithm. And the idea is that instead of trying to have better algorithms like traditionally we do in computer science, right? You learn how to do store data in n squared, and then in n log n, and then after with some assumption you have all of n algorithms. We have papers that keep improving the algorithms. But here the idea is let's just use the same algorithm A, but compress the data. So we have n points originally. We show that for every n points that they give me, I can give you back log n points. And if you run the algorithm on log n points, you get the same result, or almost the same result. So if the original algorithm was 2 to the n, and now n turned into log n, the running time is 2 to the log n. But 2 to the log n is n, so we have linear time algorithm. So this is a totally new way of thinking about computer science. Let's just use the existing slow algorithms, or your favorite heuristic without proof, on the compression. And then we can beat the state of the art using the state of the art. So, yeah, I will explain why we want proof of guarantee. So what proof of guarantee means that we need to prove that C will always be small. So it should work for any data set in the world, no assumption, no distribution, any n set of points or vectors or people, whatever. And for any such set, we need to prove that we can find such a small set. And the proof should be on the size of this compression. And since we usually pay something for the approximation, there is usually trade-off between the approximation and the compression. So for example, we say that we have 1 plus epsilon factor approximation, but you need to take a course at C of size 1 over epsilon. So if you want almost 0 error, 1 over epsilon will be huge. You probably take all the points. If you want 50% error, 1 over epsilon is just 2, so you probably take just a few points. So the trade-off is usually between the compression size and the quality, and you want to show that to prove that there is good ratio between these two. The problem here that I didn't define exactly what is a coset, what's the property of the coset. And actually the number of definition of coset is very similar to the number of papers about cosets. Because every time that we saw that we find the right definition, we see that it doesn't work on a new problem, so we invent a new coset. And some people, especially for study, complain about this because people use it as a general word for compression. So when you hear the word coset, be suspicious. In every paper, in every context, we have different definitions for coset, but the philosophy is very similar. And actually, there are some experts in coset that don't know what is coset, because it was invented in several communities using different techniques. And all done, just few courses. This is just courses that I was involved with. You can find a lot of other courses today in the web. So you see the classic problems in machine learning. We have k-means. You also have k-median, k-segments for signal processing, k-line means for approximating lines, courses for LSAP, SPCA, or SVD, so subsurface approximation. We have courses for Google PageRank, essentially for the largest eigenvector, mixture of Gaussians, and we have a lot of applications for video, for robotics. I will try to show you, again, for motivation, what we do these days with the corsets. I think that one of the corset is really amazing and very practical, and the theories are really, really nice. So there's no one hammer. Every paper, we have different techniques, because for every problem, we need some different approach. It's kind of like approximation algorithms. So we don't have one single approximation algorithms, although we have techniques. We have linear programming, we have PCA, we have some techniques how to optimize derivation for school, but there is no general algorithm for approximation any problem in the world, and that's why intuitively we have different corsets and we need different technique for every problem. Corset is some kind of approximation algorithm for the problem. And unfortunately, the corsets came from the computational geometry community, which not too many people read the papers these days, unfortunately. And it got stuck. So a lot of people, I see practical people from machine learning, don't have access to these papers, they cannot understand them, and people don't use them. But more and more now, and minimal students in the recent year, we try to implement this course set and incorporate with companies like Microsoft, hopefully soon with Google, to actually implement this process and have open source that everyone can, without doing all the complicated proof, can test it on his or her data. And I think change is going to change in the recent years, and you see the papers moving from the theoretical community to the practical community in the recent years. And I hope that this lecture will help to improve the situation. If you have any questions during the talk, please just shout or feel free. We have time. I'll be glad to talk about subjects that specifically interest you. So the original motivation for CoreSet was to improve running time of theoretical algorithm, like I said. But these are actually, most of the courses are for problems that people are quite happy with the heuristic that solve them, even if they don't have proofs. And the main motivation for using CoreSet is for dealing with big data. So what do we mean by big data? So usually we have a lot of data, high-dimensional space, and it's come on the fly. And what we need is streaming algorithms that do not store all the data on the computer. So the input is essentially infinite stream of vector, and you need to update the model. But unlike online algorithms, you're not allowed to save too much of the data. You have only something called log-n space. Most of the courses they run with on Amazon Cloud. We have about between 200 and 500 computers, and you want everything to run in parallel. So you want both parallel and streaming algorithms to use the cloud and data on the fly. And we want the code to be simple, so we can, for example, run the algorithm on GPUs, and we actually want to implement them. So we don't want to have too complicated algorithms. So there's the question: what is big data? Some people say terabytes is big data. People said even zettabyte is not exactly big data. So since we have provable results, the way I define big data is that the big computation model is essentially the streaming model and the parallel computation model, which means that the input is infinite stream of vectors. We have one pass over the data, and n is the number of points or vectors or samples that you saw till now. And you're allowed to use only log n memory during the scan. So log n is small. Even if you Google, log n is quite a small number, right? Number of atoms in the universe is, I don't know how much, 2 to the 400. So the log is just 400. So log n is a small number, you should know it by now. And if we have a lot of machines, or computers, or threads, or whatever, we want that the running time, the update time to a new point, will be divided by the number of machines. If you have 2 machines, the time should be half to run. This will prove that we actually take advantage of the thing. And the nice thing is that we don't need to take all these sophisticated parallel algorithms classes. So from what I remember when I tried to debug the algorithm that I implemented in these distributed computing classes, when you have a bug, which was the best thing is to just delete all the code and start again from scratch. I don't know if you took this course. Most of the class actually agree that this is the best thing to debug things. Just you don't have a chance. It's so complicated. So fortunately, because we don't have this problem, it's very related to the approach of Hadoop. Actually, you can implement courses using software like Hadoop, and today we work with MATLAB. We have now we are lead out of MATLAB for the big data toolbox that actually run on Amazon Cloud courses using just a few lines of code. I will try to talk about it maybe on the last lectures, but it makes things very, very easy, especially because this construction that we'll talk about will be inversely parallel. Inversely parallel means that you just have one algorithm and run it independently on each computer returning the data, and that's all. There's no interaction between the machine. It's very easy to debug things, and it's very easy to check the result in this framework. So what is exactly the type of course that we have? There's no general definition, but what are the examples we have? So the classic example is that the original course that I think was about subset. You give me n point, and the log n is just a subset of the input, and you prove something about this subset, the code. Or usually log n over epsilon, where epsilon is the approximation error that you want. So again, if you want smaller error, you need to take larger course. Over time, actually, we say why to take subset. For a lot of problems, we said you cannot find subset, but there is a small set that you can compute, which is not a small subset. For example, take the points and project them on random subspace, like in Johnson-Lindenstrass lemma. So reduce the dimensionality, you get new points, they're not part of the input, but low dimensional space, and you have a lot of properties that you can prove in this kind of dimensionality reduction. Then when we have, when you want to solve problem by k-means, then essentially, suppose that you have minus a point here and 1 point here. So a good concept intuitively will be, take 1 point, this point with weight 1, and 1 point here with weight million. So every point have a weight that represents how many points you represent in the original data. Makes sense, right? So this is why we have to use weighted subsets, where every point has a weight, how many points you represent in the original data. Again, intuitively, millions of points near each other, just replace them with 1 point with million of times the duplication of this point. This is the weighted subset. Usually, we also find out that sometimes for approximating the cost, we need an additive weight. So take the cost of that spend 100, or some strange numbers like this to approximate the original cost. And again, we have different kind of cost definition of the property of the cost. This was the construction and the type of the cost, but what we can guarantee on the courses. The most general version is what is called strong cost. So usually we assume that we have a family of queries, decision trees, supported vector machines, neural networks, lines, courses, whatever. So if you have a family and you want to find the best one in the family. So strong concept does talk about the best one. Just say that for every query in this family, for every shape, the cost, the sum of the distance, or whatever cost defined on the course set is approximately the same as in the original data. So it's for every feasible, it's approximately any feasible solution. This is what I call strong course set. It turned out that if only one is to approximate the optimal solution, or find the optimal, the best one of your data, we can have much smaller course sets, and sometimes we call them weak course sets. And during the recent year, we actually have some small sets that all we know about this set is that they contain some good approximation of the optimal solution. So we just reduce the data for this point and start to search a solution for this small space, but we cannot say something directly about these points in the connection to the optimal solution. That's just the space that is spanned by them contains the optimal solution. And not not too much, but we have at least 2 types of private courses. So private means in the term of differential privacy, which is very hard theoretical guarantee from the crypto guys on how to preserve privacy of users. And private courses usually mean that not only you compress the data, but you cannot learn almost anything from the original data based on the courses, but you can still solve the optimization problem that you want. The first course was in stock 2009, I think. And we tried to implement it again very recently. Maybe the most common courses that people use without quality courses is just uniform random sampling. So for example, in this paper, we want to do image noising. So you get a noisy image, and you want to clean the noise. So we took one of the state-of-the-art algorithm called KSVD. It's kind of a dictionary learning algorithm. And it works only on, it's working MATLAB, works only on small data. And the author suggested if you have large data, all you need to do, take random sample of the image, and then run algorithm on the random sample. It will give you the structure of the original image, and it will be good enough. And this is in general probably the most popular concept that you also use in your life. So if you give an engineer terabytes of data, and the algorithm can only support a few megabytes, what you do, just do random sample for the original data, read the model on this random sample, and hope that it will work on the full data. This is a good model for the full data. What is wrong with this approach? So actually, you can prove a lot of nice things, Chernoff-Hofting bound. You have a lot of bounds of why random sample is sometimes very smart things to do. But in what cases random sample, uniform random sample, is not a good representative of the data? Any idea? In what cases random sample probably won't help you? Yeah.
So the data is immense, like or very heavy tail.
Yeah, exactly. So for example, outliers. So you have a lot of points here. You want to do clustering of this data, and you have here clustering in the infinity. It's a very small cluster. But this is the important cluster usually. These are the terrorists. These are the rich customers. This is the popular user or customer. But you actually want to find these guys. This Ruby database, or this Ruby world, or whatever, and you want to find them. So random sample is good for marketing to know what is the mainstream. But you see, if you have minus point here and 5 point here, you won't find these 5 people using random sample. In Corset, we're allowed to use linear time algorithms. Sample actually is very fast, right? Because sample is actually sub-linear time. If you have all the data, you have random access machine, you just take record number 1 million. I mean, you just take random sample and sub-linear time sample from this point. Corset are not that fast. In Corset, the deal is that you're allowed to have one scan of all the data. You remember, we have end vectors, and you scan them, so you're allowed to see every input. Once, you cannot go back, but you're allowed to see every input once. And you're allowed to look at all these points and scan them, and then tell me what is the right Corset for this problem. So it's take linear time, you see all the data, it's not just sampling, but then you have a chance to get this guy. And we reach and say, actually, I think these guys are outliers, and I want them in the Corset. But again, how to do this provably, and how to manage. We don't assume anything about the order that you get the data or you scan them. But we still want a provable guarantee that we'll catch these guys. For example, if you want to do clustering for this data. And this is the main difference between, for example, uniform random sample and Corset. So what we do instead is we, for example, in importance sampling, we define distribution on the points. Instead of uniform random sampling, we use non-uniform random sampling. For example, if you have minus point here, 1 point here, you need to sample this point with high probability, and any point here with low probability. So each point here will be chosen with very low probability, but since you have so many points, you'll probably choose one of them. This one is only one, but you have probability of half to choose it, so you'll probably choose it eventually. And the weight is kind of inverse proportional. Again, we'll talk about the theory, but I just try to give the intuition. This guy here will have weight 1. This guy and very high probability. Every guy here will have very small probability to be selected, but when you select it, you will get very high weight because it represents all this community. So that's why we have time of sensitivity, what's probability to choose this point, how it's important to take this point to the Corset, and a multiplicative way, how many points you represent, which is what whenever the sensitivity. And of course, the problem is how to choose this important sampling. And it's interesting, when I talk, for example, with, I think during university, for example, with a professor that have a lot of experience about k-means. And when I told him about the Corset, he said, of course, just use sampling, and then solve the problem. And I explained that random sampling won't work, and he said, of course, you need to choose non-uniform random sampling. That's what we do here, then you solve the problem. And I was a bit shaky, maybe there's another community that already solved the problem, and I just reinvent the wheel. But then when I asked, what is the exact distribution? Now we're in problem. And then it wasn't clear. And this is that when we solve, we have provable results for such famous problems, usually a lot of smart engineers already thought about the direction, but they didn't know exactly how to calibrate the machines and the parameters, and they end up sometimes with millions of parameters and rules. In theory, sometimes we just add for this distribution just 2 numbers in MATLAB, so add 1/n to the popular heuristics, and that's all. Sometimes take a year or 3 years to add, but in the end of the day, you just change the distribution. Of course, after you make the change, everything makes perfect sense, and you saw the engineers said, of course. But this is where the theory helps us to actually nail down the right parameters of the data. So, for example, in this case, the classic heuristic for k-means was just find a good approximation or some heuristic to find the best cluster, and then sample the points based on the distance from the center. So points that are very far from the center should be selected with high probability. Points that are very close to the center shouldn't be selected with too high probability. And the only things that we did in the first paper was to add to the distribution 1 over n, or more precisely 1 over ni, when ni is the size of your cluster. So it turns out that, for example, if this cluster is in infinity, very far, even if you're very close to the center, we want you in the core set. So the rule was, we need to point that are either very far from the center or very close, but contained in a small cluster. The distribution depends on the distance to the center plus 1 over the size of the cluster. If you're in a small cluster, you'll be selected because of the second term. If you're in a very large cluster but very far, you'll be selected because of the first term. Again, we do the exact analysis later, but this is just an example of how we change the practical heuristic to get better result both in theory and practice. And for the problem of the image, you see, for example, in this image, if you do random sampling from points here, or patch, usually you just small squares which they call patch and sample, to get an approximation of the image, it will be a bad idea because you miss only important points here. When you run our algorithm, the courses, after we learn the KSVD problem and what exactly trying to minimize, you can build courses for this problem, and the courses essentially choose points, non-uniformly at random, and most of the points will be selected from here, and very few points will eventually be selected from this area. And then again, we run the existing algorithm, the KSVD, on our courses. And this is also a very strong issue because in the beginning, we just say we have better algorithm than the state of the art. But what happened is that, especially when we submitted the papers to other communities, they compare why didn't you test it with all these million heuristics, including the WIMG compression algorithm that they invented last week. And no code in the web, of course. You need to implement everything. And you need to have years of experience to convince the community that actually you have better algorithm. But what we now do, which makes more sense, is that we say, take your favorite algorithm, heuristic, and run it on our core set. So essentially, what we do is we take the same KSVD algorithm, run it on the core set, and compare the quality to our compared to running the algorithm on the full data in our core set. And if someone thinks that there's a better algorithm, you can just run it on the core set instead. So all I need to prove is the compression is good. Even if the heuristic have no proofs at all, that's okay because the community also believes it works. So we have proof for the compression part, and then you just use fast heuristics on the core set. So you don't really need a proof. And that's also a good combination between the theory community and the practical community. So if you're just saying, oh, this problem is NP hard, you cannot solve it, it turns out for a lot of problems that are NP hard, especially in machine learning like clustering, in linear time we can compress the data without solving the problem. So we still have the problem how to solve the optimization problem on the core sets, but now we can use heuristics or exhaustive search. Usually it's heuristics because exhaustive search is too slow, but this is a nice trade-off between heuristics and theory. And again, we beat the state of the art using the state of the art. But maybe the very surprising thing is that the theorem proved 1 plus epsilon approximation. In practice, what you get is 1 minus epsilon approximation. I mean, minus, not plus. So when we run the heuristic on the compression, we actually get better result and better model compared to what happened when you run it on the original data. And again, we test the model on the original data, essentially. We just compute the model on the core. How can it be that you compress the data and you get better model on the compressed data than the original data?
The original data may have some noise or something, some noise.
Yeah. Exactly. Yeah. So again, if you want the optimal solution on the original data in the core set, it can't be better because you already have the optimal solution and you use the information, so you get 1 plus epsilon approximation. But you basically just find some local minima, and there is a chance that the local minima that you find in the course will be smaller. And this is an open problem, maybe for you, but we don't really know why it happens. The intuition is yes. The people explain that, most of the users just find the local minima. So they get trapped in local minima, but the course kind of smooth the data. Because you don't have so much data, the function is much smoother, and that's why you get trapped in much better local minima. You don't have all this noise. You kind of remove noise, people say here. But unlike all the other stuff that I said that I can prove and explain, this is more like intuition. We don't really know when and why the course is actually vetted for a specific heuristic. It will be interesting to research that problem. Yes, please.
So going back to your point about feeding the state of the art, using the state of the art, what prevents you from repeatedly applying courses in that case? So like taking courses and then that doesn't seem intuitive.
No, it's a great question. So if I understand you correctly, you say that after I have a course, compute courses for the courses?
Yeah, it's just, yeah.
Yeah, so actually this is exactly what you're going to do, in some sense, in a few minutes. And this is a project I see a lot from engineer, but so in some sense it does make sense. Why? Suppose that I said, let's take 100 people, run a uniform random sample for people in California to understand what is the average salary of California. And then you say, I have an idea, let's sample 1,000 people, and let's then sample again 100 people from this 1,000, maybe it'd be 10 from this 100, but it doesn't make sense. I mean, sample from random sample, for example, doesn't make sense. If you're happy with 100 people, just sample 100 people. That makes sense to sample 1,000 and then select 100 from this 1,000. This is kind of the Chernow-Hofting inequality that we'll talk about, the guarantee. So there is a trade-off between the size of the sample and the error. And you need to give me what is the size that you're willing to take. This is the error that you'll get. There's no point of resampling again, unless we want to compute the courses independently in parallel. So I think we're going to get there. So the main trick will be, I'll just answer this question because it's the main idea behind course sets. So most of the courses are just method code which run on one computer, and it assumes all the data is in memory, and it sometimes even takes n squared time, which is opposite than all I promised you before. But the trick is this. What we can do, and this is based on this great question here, we can compute compression on one data set, compute the cost on another data set, and then take the union. After we take the union of these courses, the size is double. We can do the same for the other two sets, two courses, compress them again. But the problem is now eventually we have too many compressions in memory. When we have two compressions, we compress the data again. So it's kind of binary tree of compression. It's kind of a merge and reduce approach, very classic from the 70s and thinking in computer science. Just run your slow algorithms independently on each computer and each machine in Amazon, then collect all these compression. You have a lot of compression. If you want, you can compress them again. But that's it. And then run on the morning your algorithm on the small data that you get. So all the night we compress the data. On the day we have a small set of data, and then we run the exhaustive search on this small data. So what kind of techniques did we have to use to compute courses? So one of the first techniques was exponential grids. Just take grids with a lot of squares, half transform if you heard about this, and take one representative for each step. So if you have minutes of point here, there will be one representative, lot of point here, one representative. And again, you can see ideas like this from the 70s, like just cluster points, they're very close by just putting cells on the data. The main question was, what is the size of the cells? What is the area? If you choose too many cells, you have too many representatives. If you choose very large cell, you have few representatives, but maybe you have a huge cluster in one cell. What courses try to do is try to have grids that are optimizing the size and the resolution to have provable guarantee, and this was probably we'll talk about in the next talk. The other approach based on random and non-uniform random sampling, already mentioned them. You find non-uniform random sampling, random distribution on the data, and then take non-uniform random sample. Other techniques are based on deterministic algorithm that is kind of greedy. Take a point, take the farthest point for this point. You have two representatives. Take the farthest point from these 2 points. You have third representative, and continue until you don't have more budget for more points. This should be a good representation of the data for some problems. So this is called rather the state of hill climbing algorithm related to the Frank-Wolf algorithm. In some sense, PCA, principal component analysis, works this way. Find the largest singular vector, project all the points on the orthogonal and continue recursively, so it's kind of greedy. And actually, a good approach to first reduce the dimension of the data is project the points instead of random subspace on the first principal vectors of the data, first principal components, and then try to solve the problem there. And the last technique is called bicriterial approximation. So the problem with, for example, the importance sampling that I presented before was here, right? So I tell you, find the optimal solution, and then sample point according to the optimal solution. So if you have minus point here and 1 point here, first find out that there are 2 of the data, and then sample according to this cluster. But you have kind of chicken and egg problem. Because in order to know what is the right distribution, you need to solve the problem. You need to cluster to find the right clusters. But that was the motivation for computing the clusters. In other words, usually the first step in cluster construction is solve the optimal problem and use this to find the distribution. And when people see this, they're shocked. I mean, all the motivation, the reason why they listen to you is to solve the optimization problem. And the first line, the algorithm is solve the optimization problem. What really makes sense is that we don't really need to solve the optimization problem. We usually just need some very rough approximation. It's called bicriterial approximation. This is the last line here. So again, I will talk about it more formally, but in general, you have constant factor approximation in computer science. For example, you have 1 k-centers to approximate the data. So constant factor approximation means that the cost can be at most twice or 10 times the optimal cost. This is the classic constant factor approximation in computer science. Bicriterial also means that you can take more models or more centers to use to approximate the data. And usually we can do this approximation very fast. And based on this fast guess of the right solution, we compute the cost on the data. So again, other related techniques, there's a community called Sketch. Sketch means essentially take the data and project it on some random subspace. But again, the way you choose the subspace is independent of the data now, and it's essentially a generalization of the Johnson-Linders idea. The advantage of this technique, usually they can handle update of just 1 coordinate of each point, where we usually only support insertion of points. And the disadvantage is that usually you need to assume something about the coordinates that are, for example, in the integer grid between 1 till n to the 5. You have some constraint about the numbers, the numbers that you actually can use. Another community called property testing. They're actually aiming to answer questions in sublinear time. So again, in courses we're allowed to scan all the data. In property testing, we try to answer the question by just using sublinear queries. For example, if you want to know what is the average age of the people here, can you take just several random sampling and then decide based on this, for example. But you're not allowed to look over all the data, which is quite different from the cost approach. So next, let's talk about some application. So again, in the robotics lab from IT, what we try to do is you have, for example, 1 million people in Singapore that are working with smartphones, and they want communication. And you can put, like here, you have Wi-Fi, like here you have Wi-Fi servers, but at night there's no one here. So why do we need these expensive Wi-Fi servers here at night? So the idea is that let's have moving communication servers. So when everyone at work, all the helicopters with servers will be here. When we return home, all the servers will be near the home of the people. And the main problem is where, so we want in real time to tell these robots where to go. So we need to, for this, to cluster the points. And the problem is you have n moving clients, which are the people with smartphones. And you want to find where to put the K servers, which are the quadrotors, the helicopters, such that the maximum distance for each client to its nearest server is minimized. So the cost is the maximum distance between the client and its nearest server, because we assume that every client connects to the nearest server. This is, of course, NP-hard problem, as you probably know, but it turned out that just computing costs for this problem it's very easy in linear time. So what's going on is that on real time, we just keep the representative of Singapore. And we proved that if we solve the problem of this more representative set, then we have the right clustering of the original data. So the challenge is to compute in real time the corset for all the people and choose the right representatives. Another problem is that we actually have some constraints. We actually want the servers to be close to each other in some sense. Yes?
Do you update the corsets like dynamically?
Yes. We'll talk about how to do this, but yes. So it's small corsets, but you need to update them dynamically, for example. So, see a short movie. So yeah, I tried it also in my kids and their friends. We have this working robots, try to catch them. And the winner is the one that is farthest from the robot. So the robot tried to find two representatives of the kids and solve the problem in real time. And they're moving in the room. And here you see, yeah. So this is the real experiment with the quads. So you see here the point, and you see when this guy escaped, automatically he was chosen for the corsets, and that's how we not close it. So these robots upstairs just catch this guy. And essentially, for example, if you in the beginning you have outside, just take random sample, but if someone escapes, because the property guarantee that this one will be in the representative set. Another motivation, so there are, trying to find it, that is, yeah. So there are millions of startups today with robots. That essentially suggest you to take a GoPro, which is a camera on a robot, and take a picture of you. For example, here in the, why you cannot see your nicely? Okay, we'll fix it tomorrow. It's a beautiful movie, really beautiful. But just the bottom line is that you want to put a camera on a helicopter on a quad. You want to use ski. The robot will do the ski. And I go today, when you put it here, you see everyone except you, which is really what you want in the image. But it's more than this. Think about wedding. You can put a robot that will follow the bride all the time. You can have millions of, or hundreds at least, of camera people replaced by robots. So a lot of potential these days, especially because these robots are very cheap and not so dangerous. The main problem related to machine learning that we try to solve, now you're with me, right? Yeah. So in the robotics lab in Haifa, when I try to implement this kind of robots, you buy this very cheap robot, I think about $20 in Amazon. But the problem is the robot have no idea where it is. So we need to solve a computer vision problem to find these spots, the marks that we put on the robot, to know what is the right position. So if you have a stereo image for two cameras, look at the robot. Each camera identifies the position of the robot, and that's how we can tell them, we know where the X, Y, Z, where is the robot in space. And then we can control it and tell you you need to go more left or more right. Now, what is the machine learning that is hidden here? The problem is that we have a controller that tell me where you want to go, tell me where you are, and tell you what to do. But the computer vision algorithm, you try to find this point, especially when you have light issues and you're outside, don't really know where is the robot. They have some distribution. So there are a lot of noise and outliers, and you have distribution of where the robot is. So the visual algorithm, you just take the mean of something like this and give to the control algorithm the best guess. What we try to do today is what is called probabilistic algorithm, probabilistic corsets. When instead of the input is endpoint cluster them, you get as input n distributions. So the first point is either here or here. The second point is either here or here. The third point is either here or here. It's the same with people. So Danny is not a single point in space. With good probabilities at home and with good probabilities at work. So the input is this probabilities of people or points. And now instead of minimize the sum square distance, for example, we want to minimize the expected cost. What is the expected sum square distances? So that's how we recently have, for example, in Sausage last Sausage conference, we call it the first corset for probabilistic corset for the minimum enclosing ball. So what is the minimum ball to cover all the points? But you have n distribution instead of n points. And now we try to generalize this for this kind of computer vision problems. And we take, again, the state-of-the-art computer vision algorithms to solve this problem and combine them with the controller to find the best combination to compute the closest of where probably the robot is and what points we need from all the image to approximate the position of the robot. Now, we're not talking about linear time or nonlinear time, we're talking about real time. So we have about 5 milliseconds to answer the question. So now the algorithm should be really, really, really easy and fast. And we have much more challenging courses. Again, is a great approach for solving these kind of problems. Okay, we have 7 minutes. I will mention a few other applications. So the last one is maybe my favorite one. So I actually recorded my live during the last 2 days. The camera here with a microphone, and you can't see it, but essentially it's connected to a cable also. And I record my entire life in the last 2 years. And the main challenge is that, for example, if I want to send a picture of my kids to the family, it's a big data problem. And in the end of the week, when I want to send them the picture, even if I have a real-time algorithm, it will take a week to scan all the data. So if I don't know the exact hour, I cannot find the right location when my daughter said the first words, for example. So the problem here, in general, when you talk about Google Glasses or a lot of other type of sensors these days, we can collect so much data in real time, and the sensors are more and more cheap. You can buy them on Amazon. And you want to collect the data, and you want to, for example, have a log of all the data that I collected on my life. So I can find special events, you can do traffic analysis, you can understand what are the points I usually want to visit. And for this, we implemented this system that user walk around Boston. This is a kind of a doctor which is a bus to walk Boston. And in every given moment, we collect data on the smartphone, but we send to the server in our lab only the representative point, which is the cursor. And we're totally guaranteed that you can find the path according to our optimization function based only on a few points on the courses. So in real time, the users send the data to our server, and we collect points in every given moment. We choose what is the right moment to stop, and select the best point to send to the server, and then we continue to collect data. So eventually, of course, we have too many points on the server side. We also have a lot of users. So we need to also do more compression on the server side. So we have too many courses here, so we try to compute courses for these courses over time. So it started with GPS. On the last papers, we actually moved to video data. Now we take the data from the glasses, either spy glasses like this or smart glasses, Google, and we try to understand where you move from a different scene. So we kind of do segmentation of the data. But instead of GPS data, 3-dimensional space, you have now million-dimensional space because every image has millions of points. And you want to find what are the right pictures to take to the story. And understand when we're following robots, but I think the nice thing is that when you have all the representative image, and you have all the courses for all the data, then again, you compute courses of these two courses, and again and again, and you get kind of a tree through life. So if you want a summary of a specific year, you just go down to the tree to the right resolution, and you have a summary of this specific interval of time. And it's very easy. Also, if you want something in the middle, because it's binary, it's very easy to find any continuous interval of time between in the data. And then we develop search engine for searching this kind of data. And you can see this each cluster in the course. This is, for example, representative in the course for all these points. This is representative for all this image, and so on. And we develop with this, we develop kind of an iPhone application, and now also an Android application. It allows you to Google you live. So when I want to say when it was a meeting with Alex, I can just write it down, or whether I buy books, or whether I visited Starbucks last time. You can actually write free text and get a summary of results, And other additional other algorithms like Foursquare, when you actually physically check in on Google Latitude when there is no text search, which was really strange for working with the Google application without a search line. But in general, we try to have this text line, and when you have, after you send all the data to the system, you have a summary, text summary for all the data, totally automatically. So then we take the GPS point, only the representative is sending to Google API, then translate it to text, and then we use some other algorithm to open the text, and we have totally autonomous diary of your life. And then you can Google things like give restaurant July 11. This is a real example. Or we can, you can see how much time. So we take Yelp database, and Yelp, for every store you have the category. You can see how much time I spent at home, at work, or in entertainment. This was a very hard day. If other users share the data with you, you can find when you meet specific people, and so on. And we add more and more, again, currently just support GPS, very soon it will support video data. And how to actually compute this kind of diary, we'll start talking about it tomorrow, and we'll be more and more formal, and all the things that I mounted here, or try to define formally what is actually trying to do, how we want to do this to prove, will be less fun than now, but I think that you learn much more. We have this 1 minute, and I'll be ready to answer questions. If I don't answer the question, feel free to just jump on me. I'm without the family here for a week. It's like heavens, I have all the time in the world. So please, please come and talk to me. Tell me about your application, what you want to do post for. Maybe I can help you with this. I'll be glad to hear about your work within academia on the industry. Thank you very much. More questions? Yes.
So one of the important things in text applications is the text coverage. For example, if you want to do syntactic parsing or translation, you really care about having a good coverage over all the possible words, or as much as you can. So downsampling or like format, is there a way to use it without compromising the lexical coverage?
Sorry, without what?
Compromising the lexical coverage?
Yes. So again, we use techniques for example, the latest semantic analysis, a more sophisticated algorithm that people use on text mining. And we take, for example, all the documents in Wikipedia. So a row is just a document, and the column is a word. So and it's a very sparse vector. So you have all the words in English on the columns, it's a few millions. And for every document, you have a few million documents. And you just want to write one if the word appear in the document, or 0 if not. Frequency, 10 document metrics, they call it, right? And we try to understand what the algorithm in text mining that people use, like the classic one is latent semantic analysis, or SVT, to reduce the dimensionality. It's not just random sampling, as you said. It's more smart things like this, and LDA, negative factor approximation, whatever. And then we define processes for this kind of problems to find the right low-dimensional space to contain the data. On this space, the word sandwich and the word Subway are very close, because Subway is also a store of sandwiches, and Starbucks is related to coffee. And then if you want to Google for example, for coffee, but actually you visit Starbucks, so Google API said that the place is Starbucks, but you actually look for coffee. So using Wikipedia, or in this case it was Yelp, you know that coffee is related to Starbucks, because there are a lot of reviews of people that say the word. There is strong correlation between the word Starbucks and coffee in these kind of databases, and then you compute this low-dimensional space. But again, you use a traditional algorithm in text mining that people already saw that work great, like latent semantic analysis. But the main problem was that you work only on small corpus, or small set of documents, and we show that we can run this algorithm on huge amount of documents on the cloud by first computing constant for the problem all night, and in the morning just run the inefficient algorithm. Everyone agree already that they work great, but they don't know how to compute it on large data. You just compute them on a quarter, and we get this kind of amazing result with interpretation for the people, and we then plug it back to the application. Does this make sense?
I'll follow up.
Good, please come. Yeah. More questions? Okay, so I think we're 2 minutes after time. We'll continue tomorrow. Thank you very much.
You can go on.